Welcome everybody to the last day of the meeting, and let's give the OCB office a hand for a great meeting so far. Thanks to everybody for making it out on the last day, the last morning of the last day. I hope we have a good session for you today. As Heather was saying, the title is the title. Coastal Observing Systems to Understand and Predict Ecosystem Changes. I think we got a good lineup of speakers for you today. And so the motivation for this, of course, is that as part of OCB's remit is not just the carbon system, but also the effects of changing oceans on marine ecosystems. And one thing about marine ecosystems is that despite the fact that the coastal ocean is a relatively small fraction of our global ocean, it has outsized importance for coastal ecosystems, coastal ecosystems and coastal communities. And perhaps one of the best examples of that is this plot on the left-hand side, which is just a reconstruction of global fisheries catch. And it really shows those warm colors on that heat map, which is this uneven scale. It's over 90% of the fish that we catch are in our coastal oceans, and that's, say, 7% of the global ocean. And of course, those resources are presently experiencing myriad changes, changing distributions, acidification effects, coral bleaching, and those changes are generating the need to make critical decisions about what to do in the face of these challenges. And so as a community, I think we really need to come together and discuss how to bring our expertise, our capacity to bear on these problems. And another aspect of this is that some of the observing systems that we've worked with and we've pioneered over the years are often limited and challenged in these highly dynamic coastal ecosystems. You know, if you compare the plot of fisheries catch on the left with the Argo array on the right, you know, where one picks up, the other drops off. And that's on purpose. The Argo array was built for different purposes. Susan will talk to us about this later today. Likewise, ocean color, which we've made such fantastic use of for many years, is challenged in coastal systems. You know, everyone's written that sentence in their discussion with a caveat about, take this with a grain of salt because ocean color is tricky in this shallow water. And so, there's a number of overarching questions we'd like to wrestle with in today's sessions. What are the core observing needs for understanding and monitoring coastal ecosystem change? And what are the core needs for informing those decisions? Providing actionable information that we can help our managers and coastal communities make the decisions they need to make. How can we better harness existing and nascent technologies to meet those needs? Which advances in observing technologies are most critical for understanding and predicting ecosystem change? And what mechanisms, funding, technology transfer would improve the translation of the OCB observing expertise and capacity to improve coastal ecosystem understanding, predictions, and decisions? We have a great lineup of folks today to sort of walk us through some of these challenges and perhaps raise new ones that weren't in those questions. We're going to lead off with Jon Hare, who's John, you get a longer title every week, it seems, but he's the NOAA NIMS Director of Scientific Programs and Chief Science Advisor. He's on loan from his normal post as the Director of the Northeast Fisheries Science Center, just down the street here. And so he's going to talk to us about coastal observing systems for resilient marine resources and changing climate. Someone working on the front lines of those decisions, but also someone with a lot of background in ocean observing before moving to his present esteemed position. And then Susan's going to take us and tell us a little bit about the lessons learned from pulling together the community to meet this global observing challenge with the Argo system, and of course, probably touch on some of the extensions to BGC Argo and other areas. Think about how that might be applied to coastal regions, those lessons. And then we're going to have a series of talks that bring us through some of these nascent and emerging technologies. Susanne Craig from the Goddard Space Flight Center is going to take the remote sensing side. This is sensing from above, satellites and unmanned aerial vehicles, and talk about the advances that might help those be more and more useful in coastal waters. Then we're going to have an all-star team of folks that are going to cover this broad scope of in-situ observing technologies, with short talks from Adrienne Sutton, looking at surface autonomous technologies for the coastal ocean. Saba is going to take us through eco-gliders going under the ocean surface and their capacity to help meet this challenge. And then we're going to bring Alec Wang back up, and he's going to tell us about a new effort to team up with the commercial fishing community to provide observing capacity. And this is actually there's a recently supported OCB activity on this front that Alec will talk about and provide some information about how to get involved if you're interested. And then we're going to have Clarissa Anderson, who's the director of the Southern California Ocean Observing System, come and provide her perspective on what a next generation coastal observing system might look like, and then move to a discussion section where we can perhaps return to those overarching questions. So without further ado, I'll get ourselves back on time and invite Jon Hare up to lead us off. This is the
Thank you very much. Nice to be here. Thank you for the invitation, Charlie. This is my first OCB meeting, so I'm a newcomer here. And my strategy was to try to figure out what you all are interested in, and then think about what perspective I might have that could be interesting to you. So kind of take it from that approach. Okay, so again, I'm Jon Hare. I'm a fisheries oceanographer by training, so looking at the interaction between oceanography and fisheries. So, several trophic levels higher than where most of you focus your time. I've worked in the Caribbean, all in the Atlantic, Caribbean, Gulf of Mexico, Southeast, Northeast U.S., Canadian water. And I made the transition from an active scientist to a scientific administrator in 2016. And there's pros and cons to that, and I'm happy to talk about that if anyone's interested, but not for today. So just an outline for what I'm going to talk about today is, again, as I said, I've tried to find out a little bit about OCB, the community, what your goals are. So I'll just sort of talk about what I learned, sort of my perspective, and then run through sort of three pieces. One is this idea of science to inform policy. Charlie, you mentioned that in your introduction, sort of the importance or not importance of that. And then I'm going to talk a little bit about the structure of science, how I see the structure of science working to inform policy or to make progress on scientific questions. And then talk a little bit about opportunities going forward that I see for you, the OCB community, to work with me, the fisheries community, as it were. So again, you have a very nice website. Whoever does OCB's web design, very good. Thank you very much. Woo! It's very easy to try to get. It's very easy to sort of find out. It's much easier than our website. So maybe we need to hire you. But again, you have your accomplishments and then sort of the science that you're involved in. You've got the ocean chemistry, carbon uptake and storage, carbon fluxes, changing marine ecosystems, ocean observatories, and biological pumps. So my training in oceanography, I understand what all of that means. I'm off to a good start in terms of understanding what you are up to. The idea of OCB, this community, is to coordinate and oversee activities to advance high priority research areas. And part of this is ocean observations from multiple platforms spanning a wide range of spatial and temporal scales. So it's sort of community-driven research questions with a strong component of observing the ocean ecosystem. And then, although you do not actively participate in policy implementation, you or it, OCB, coordinates and compiles scientific input from the research community to inform effective policy. And Charlie talked about that. What is the role of science in informing policy? How do scientists inform policy? So I want to just sort of, think about this bottom-up organization where research questions are driven by the community, and then how that bottom-up organization can then inform policy decisions. And when I hear that conversation, when I hear your goals presented that way, I think very much of sort of NOAA fisheries science. We are a science organization, not so much community-driven questions, but research, observations, with the idea that that information will be used to inform management. It's actively used to inform management. I spend half of my time on the informing management side, and half of my time on administering the science to inform management. So OCB is, a bottom-up research and observations to inform effective policy. NOAA Fisheries, where I work, I would argue is sort of a top-down science to inform management. And the commonalities in these two pieces are it's science and it's this interest or intent in informing policy or management. I want to talk about sort of those two elements, the science and informing policy. And I'm going to start next is sort of how does science inform policy? There's a lot has been written on it. There's a lot of resources. I know many of you are involved there. I'm just going to highlight sort of three pieces. One is an article from Nature. One is a sort of perspective piece that I wrote in 2020. And then the last is just a very simple analogy that, for me at least, sums it up. So the Nature paper by Rosen, how does science inform policy? As scientists, we need to understand how policy making works. As scientists, we need to understand the organizations and the individuals that are actively involved in forming policy. As scientists, we need to understand how science is currently being used to inform policy. We then need to synthesize our understanding. And synthesize, I think, is actually a key point. I mean, I've written, trying to explain something to somebody, and it starts out one page, 2, 5, 10. And I think, about that 10 page, I've got the details, I've got it synthesized, and that's not synthesizing for policy. It's how do you condense your ideas, so that the key element is there up front and understandable. And so synthesizing really is a skill that I think we all need to continue to work on. The fifth piece I think is really important is, as scientists, Rosen sort of informs us not to advocate for a particular policy solution, but to help policymakers develop options and help them understand the pros and cons or consequences of the options. And then the sixth one from the Rosen paper is to listen closely to the questions and needs of the policymakers and think about what they need, not necessarily about what you want to do. But hopefully there is a middle ground between their needs and what you want to do as a scientist. So then, the paper which I wrote in 2020 is very similar, and these ideas are also very similar to Elinor Ostrom's sort of concept of science to management. She's a Nobel Prize winning economist. I'm not going to go through this list for a matter of time, but the one piece, we're going to hear from Alec, talking about working with fishermen on making carbonate biogeochemistry questions. You've got sort of, recognize that people who are using the ocean are knowledge experts and really sort of engage in participatory science. We can think of science as something separate that we sort of toss over to inform policy, or we can think of science as an integral component to how we work as a society. And that's sort of the analogy that I've been, think about is the science is tennis and policy is soccer. As scientists to inform policy, our tennis players need to learn how to play tennis, how to play soccer. Science is a discipline which is largely thought of as separate from many other things. If we want science to inform many other things, we need to understand those things and be conversant in that game as well as our science. So, in terms of science to inform policy, that's what we do in NOAA Fisheries. We work a lot with our stakeholders and partners to translate that science. I think there's an opportunity for you all to do the same. So now just talking about the structure of science, reading through the OCB website, I see that there's a real interest in observations and a real interest in process studies or research. And then there's obviously this technological innovation, very much, build a scientific community around these building blocks, and then this idea of synthesizing knowledge for policymakers. So that, in fact, is one part of the sort of the scientific model that was developed during the GLOBEC program. global ocean biology ecosystem components. I don't quite remember what GLOBEC stands for. Who knows? I saw Dennis McGillicuddy. What does GLOBEC stand for, Dennis? Okay, thank you. Yeah, it's too far away. My glasses don't work at that distance. Yeah. So this is the model that the GLOBEC community developed, and I see elements of that model in the OCB community. It's this sort of triangle of research informing modeling, modeling informing observations, observations, retrospective analyses, forming process studies, and sort of working among these three components. Technology can drive this, and you synthesize and you build scientific communities. So there's real sort of historical connections in terms of how we do ocean science that I see in the OCB community. Now, if I'm going to look at what I think NOAA Fisheries, how NOAA Fisheries works, the only piece that I would add is this very strong connection to policymakers. It's a two-way arrow. We work hard to understand what their questions, what their needs are, design our science around that, and then provide it and work very interactively. So I think, when you're thinking about OCB and functioning, I would sort of, I know you all do, broaden your view to really think about sort of the collection of activities that are necessary to be successful. So then, if you think here's, OCB strengths are in red, I would argue sort of NOAA Fisheries strengths are in blue. I know there's a strong component of modeling in the OCB community, so that one perhaps should be red too. But when I look at this, I see that there's a lot of overlap, a lot of synergy, a lot of opportunity to collaborate, a lot of opportunity to work together, strengths of both communities. And so that's what I want to just talk about a little bit now, is where do I see these overlaps? Where do I see the opportunity to work together? Again, from my perspective, my job is to do science to inform policymakers. So how can we work together for both of us to inform policymakers? So here's another wonderful graphic from your website. 6 sort of areas of interest. You've got changing ocean chemistry, ocean carbon uptake and storage, estuarine and coastal carbon fluxes, changing marine ecosystems, biological pump, and ocean observatories. These 2 in the thicker red, I think, is where there's real congruence between what we do in NOAA and what you, OCB community, are working on. These 2 in sort of the lighter red, I would say moderate congruence. And then these 2, I very much see the relevance to societal challenges, but the relevance to sort of the NOAA day-to-day is less. Not saying it's not important, just saying there's less relevance, less opportunity for collaboration. So why, sort of fisheries, there has been a lot. I think Dwight Wijffels here, there he is, Dwight, Deputy Director of the Ocean Acidification Program, very supportive of NOAA Fisheries and research to understand the link between ocean acidification and fisheries production. Why is that relevant? Fisheries, sort of the dockside value, fish sold from a boat to a dealer, 4.8 million. A tenth of that is scallops in the northeast alone. And scallops are a bivalve, highly susceptible to ocean acidification. Then you've got a range of crustaceans, crabs, lobsters, and shrimp. Ocean acidification effects on crustaceans is not quite as clear as it is on bivalves, but you're, another tenth, another tenth, another tenth. So arguably 40% of our national fisheries production is dependent on species that are either directly affected by ocean acidification, bivalves, or potentially affected by ocean acidification, crustaceans. And then the rest is in fish. Salmon is another tenth. That's where 50%, and then wild capture fisheries are the other 50%. So there is a real interest from the fisheries perspective as to what are the effects of ocean acidification on these animals, what is the effect of ocean acidification on these populations, what are the effects on our ability to sustain these populations going forward for healthy marine ecosystems and fishing communities. So we've been working NOAA Fisheries with others, modeling the effects of ocean acidification on the Atlantic sea scallop fishery. and then modeling the effect of Atlantic sea scallop socio-ecological systems. So going from the chemistry to the biology of scallops, to the population of scallops, to the fisheries of scallops to the economics and community effects of the scallop fisheries. So really working to make that sort of range from OCB type activities and directly connecting it to communities and people who use the ocean. And I think there's, this is one example. I think there are a host of examples like this, opportunities to play out and connect to the sequence. The other area is in the ocean observation piece. Many fisheries regions, many regions in the United States have long-term sampling programs, largely vessel-based. In the Northeast, we have our ecosystem monitoring program. They're deploying rosettes for nutrients, carbonate chemistry, eDNA, and other water sample type measurements in addition to net CTD. And these are going on throughout the seasons and have been repeated over a number of years. So there's a lot of data and opportunity to collect additional data in these sampling. Some of the NOAA research vessels are also outfitted with the sort of flow-through PCO2 systems that are run through AOML. This is the one track on our NOAA ship Bigelow. She'll make 4 or 5 coverages of the ecosystem a year. Instruments were deployed maybe 2010, so we're upwards of 10+ years of this sort of repeated coverage of the ecosystem. So there really is an opportunity to think about what are the long-term, or not long-term, one decade changes in carbonate chemistry in the system. And this is, is also occurring in other systems. And then, going to that point is, the NOAA Fisheries has been working in these ecosystems for decades. The CalCoffee program, which is a California current program, started in the 1950s and is ongoing today. The EcoMon program in the Northeast started in the 1970s and is ongoing today. There certainly are challenges in terms of the cost of making shipboard observations. I think that's a challenge that certainly we're struggling with in NOAA, and I think all of us are struggling with. So how can we use new technologies? How can we use different ways of measuring things to continue these observations for the period of decades, which is really what we need to understand how these systems are changing. So there is a lot of opportunity for collaboration to work together on these previously collected data sets and to think about how to leverage into sort of new technologies or extending time series with additional measurements. Another way for us to interact are what we call ecosystem status reports. So every region, Alaska, California current, Gulf of Mexico, Northeast, West Hawaii, Pacific Islands, Southeast U.S. are now within NOAA producing ecosystem status reports. These status reports are an attempt to sort of synthesize the current state of an ecosystem broadly, from chemistry to people, through all those steps we talked about before. There are varying degrees of detail depending on the amount of data available in any particular region. This is a plot, I think, Dreux Saba, I think you put this together for the Northeast ecosystem status report. It's looking at a compilation of carbonate chemistry water samples made, I think it was from 2008 to 2019, Grace, roughly. So again, trying to bring in this information into an ecosystem context. These reports are then provided to the NOAA fisheries stakeholders and partners. So they're the regional fisheries management councils, the state marine fisheries commission, the state managers, other federal managers, to try to bring this understanding that ocean chemistry is as important to marine ecosystems as, say, temperature, or as, say, changes in salinity, and try to help understand that, it's an ecosystem that we are dealing with, and your ability to use that ecosystem at one end is affected by these sort of basic physical and chemical and biological changes in those ecosystems. So there's a lot of opportunity to contribute to these ecosystem status reports. And this last one is But Charlie showed the plot of fisheries production. And he showed that, fisheries production, the amount of biomass of fish that is removed from an ecosystem is concentrated in shelf regions. And I think that kind of makes sense to all of us. This is a recent paper by Kevin Friedland, shows the trend in chlorophyll from 1998 to 2009 globally. Red is decreasing, blue is increasing. So most of our fish production is in coastal continental shelf ecosystems, and many of these continental shelf ecosystems have decreasing chlorophyll. So, when you think about that, fish production, ecosystem production has to be linked to primary production. And if our primary production is decreasing, what does that mean for fisheries production? If primary production is decreasing, what is happening to the carbon in those? Where's the carbon going? It's not quite like physical, heat conservation, but carbon's got to be going somewhere. Where are the nutrients that had been fueling the phytoplankton in 1998? Where are those nutrients going? We used to take hundreds of millions of tons of cod out of the Northeast shelf ecosystem in the 1800s, 1700s, 1900s. Now the fishery is at like 5 million metric tons. Where did all the support for 95 million metric tons of cod, where did it go? How does ocean productivity link to fisheries productivity? How does it link to marine mammal productivity? How does it link to higher level trophic productivity? And then, because that's where humans really engage with these ecosystems, is through some of these higher trophic levels. So helping us understand the causes, the consequences of these changes, and helping all of us think about what that means for marine ecosystems. I think there's a lot of value there for us to work together. So again, I think, in terms of marine ecosystems and ocean observatories, there's just, any number of ways we could work together. This changing ocean chemistry and estuarine and coastal carbon fluxes, didn't talk too much about that, but I think there is opportunity. And then, the biological pump and ocean carbon uptake and storage is more of a, climate mitigation type question or climate adaptation type question, certainly of interest to NOAA fisheries, but not as squarely in our sort of directed activities. So this is my last slide. OCB, again, we sort of describe yourself as a bottom-up research and observing to inform effective policy. So I'm always sort of interested in this idea of bottom-up science and top-down science. And I think when I hear top-down science, I think of an individual or an organization sort of dictating what science will be done. But another way to think about top-down could be, we want to inform this purpose. What science does this purpose need to be informed? So it's not a nation or an individual that's sort of a top-down science, but it's a purpose-driven science. So I think there is more, I think top-down and bottom-up are more complementary than I think of they are, certainly. And so in terms of this, purpose, how are we going to mitigate climate change? How are we going to adapt to climate change? And then we've got the marine resource management questions as well. So, a question, something I'd just like to challenge all of you just to think about is what would a more top-down, however you want to define it, what would a more top-down OCB look like? What problems would this community like to work on and structure around that aren't simply, scientific interest, but connected to this outcome, sort of societal impact outcome type problems. There's certainly a lot of them out there, and they're certainly important. So thank you very much for your attention. I've got a few minutes for questions. Thank you.
Yeah, so thank you, John, and questions. Yes. Catch John now, because he's going to have to run a bit early for a congressional briefing, so
not that
fire away.
Well, quick question, John. Thank you very much. I'm Mike Roman, University of Maryland. You remember the CAMEO program, which was I see you're laughing like many of us are, which was an attempt to kind of get the academic community engaged in some of the questions that were important to NOAA. What are the prospects of resurrecting a program like that to get the OCB community involved?
I'm an optimist, so the prospects are good. But I think we need to learn our lessons. I don't know how many of you know Cameo, just have heard of it before, right? So, Cameo was sort of a program largely between academics and NOAA that came after GLOBEC. My opinion, GLOBEC faltered because it always expressed the intent to inform management and policy, but largely fell short. So the disconnect between sort of the bottom-up driven science and this purpose-driven science that NOAA needs, that split was formed. And then the Cameo process, it just accelerated that split. So I think we're far apart, but I think we've learned our lessons as to what we need to do to be effective to come together and work, NSF, NOAA side by side. So I think I'm an optimist. I think it's time to have those conversations again about what would we do if we were to work together. I think Cameo and GLOBEC are excellent examples for us to learn from.
Let's see, I saw one up there and then down to Susanne. White back there.
Or something after that? No. Jon, thanks so much. Great to hear from you. So I'm wondering if we could speak a little bit. So I'm a mechanic at nature, and I love the diagram which lays out all the science capabilities, and then we put a little bubble that says policy, and we've got that arrow, and we blow over that arrow. Like that's that arrow is the gap that we speak of. That I would really like to have a clear, and we're trying to do this, I think, between our program and fisheries and others. But if we could unpack that arrow a little bit to understand the specific mechanisms, what are the vehicles? There it is. There's that arrow. So you talk about ecosystem status reports. I mean, that's a vehicle, that gets generated. That's a product that gets delivered. How can the OCB community? What form could they contribute? My sense is there's a lot of science that's been generated at OCB right now that could very well be applied and lens through application to policy. So it isn't even like reorienting OCB. It's a question of mining its science outputs in a manner that's more relevant to policy. So I think I'd really like to unpack that arrow. So.
I mean, it's two ways to do it, right? One is for this community to understand it, understand the mechanism, understand how it works, really dig into it. The other way to do it is to collaborate with groups that know how to do it and do it every day. And it's similar, we've had the conversation with OAR, climate modeling. Does OAR need to learn fisheries management to understand how to apply climate models to fisheries management? Or does OAR need to work with NOAA fisheries? NOAA fisheries already has the understanding of how fisheries management works. So I would argue, you've got two choices. Learn it yourself and do it yourself, or find people who do it every day and work and collaborate with them. In terms of the second is sort of easier, arguably. The first is more difficult. And so, if you're going to take the first route, think about where the science that you do can inform policy, and then take that Rosen paper or sort of my outlook, or the you play tennis and want to understand soccer, and really spend time in those processes understanding how they work. So, in terms of, you've got 6 areas, the societal outcomes from those 6 areas are very different. So you've got arguably at least 4 different sort of policy entrees. And so look for collaborators who are already working in those areas or understand how that policy is made as a community.
One more quick one.
Thanks for that excellent talk. Susanne Craig, NASA GSFC. I have a more kind of specific drill down into the details question. And in particular, it relates to how we, as a collection of sometimes pretty siloized research communities, can answer the following question, and you even said it yourself. Primary production is being fundamentally perturbed by a number of different processes. Phytoplankton phenology is being absolutely fundamentally reshaped in terms of its timing and community composition. That from ecological first principles, that must have important implications for secondary producers and size selective feeders. I've been trying to answer this question for a long time. I worked in DFO in Canada. How do we as a community bring all of those different elements together? I'm an ocean color person. I can tell you what's happening to phytoplankton from space. How do I work with my zooplankton and fisheries colleagues to facilitate that kind of quantitative understanding?
Yeah, I mean, so, you know, from an OCB perspective, as I understand, you know, you set up workshops and sponsor groups. I'm not quite sure how it works, but I'm sure it works because I see the outcome. So you could set up a group to look at the link from primary to secondary to forage fish to higher trophic levels, relatively small, and really run through the details of that and ask that group to think about how do changes in primary productivity affect. You know, so I think OCB is in a perfect place to do that. There are other groups that can do that as well. But it is, I mean, like for me, I don't even know how to formulate that question in my head. Where did hundreds of millions of metric tons of fish biomass go? It's not coming back. We have the observations that clearly show that, you know, many fish populations are not coming back to previous levels. And we also know that we have, you know, in most cases, reasonably good control of fishing. In many cases, fishing is as low as it has ever been. So where'd the productivity go? Yeah, and so I think starting to look at that fundamental question is critical for, you know, bigger, how are we going to live on this planet type thing.
But did anyone copy that down for our next working group proposal?
She did, yeah. I think she wrote it down before she asked the question.
I know that John has to disappear, so I wanted to make sure we got this one last one in from Ken Johnson. While Charlie emphasized the productivity at the coast, open oceans play a significant role for tuna, salmon at sea. Does NMFS have an appropriate focus in the open seas?
NMFS have an appropriate focus. That's a normative question, not a scientific question. So as director of NOAA's NMFS scientific programs, I shouldn't answer the normative question. But thinking of, you know, obviously we have more of a focus in the continental shelf systems. And the open ocean is, you know, NMFS is less involved there. So that's an opportunity to work together in terms of understanding what is in the open ocean. There is a lot of fishing that occurs in, you know, outside of national jurisdiction in international waters, and that's an area of a lot of illegal fishing, a lot of distant water fishing fleets in that area. So getting a better understanding of what is happening there in terms of tuna and salmon. You know, the other piece that, you know, that hasn't, I don't think it's started yet, but there's certainly continued increasing talk is, you know, utilizing the mesopelagic biomass. The ptophid, the hatchet fishes, those fascinating, you know, animals that are part of those, you know, open ocean systems. And so there is a lot of biomass out there. You know, do we want to, as a society, begin to exploit it for our consumption? So I think there is, you know, a need to be thinking out in the open ocean. You know, NOAA Fisheries is going to have a more challenging time working in international waters. But there are international organizations that, you know, probably could be compelled to spend more time there.
Good question, Ken. So let's thank John again.
Thank you very much.
The one quick sheet I wanted to plan for the discussion session is John noted sustained observations, and that fishery is doing sustained observations, and that kind of gets me thinking of a biogeochemical sort of model where there's ships of opportunity out there for the sustained observations that need to inform the questions John was talking about. So maybe we can revisit that in the discussion today. But for now, I think we need to move on to our next esteemed speaker. Susan Wijffels is a senior scientist at Woods Hole, and she's going to talk to us about meeting the ocean observing challenge, lessons from the Argo program. So welcome, Susan.
All right. Okay. Good morning, everyone. Can you hear me okay? Yeah. All right. So Charlie asked me to address you today, so thanks to Charlie. I'm a large-scale physical oceanographer, and I've been working mostly thinking about the ocean's role in climate and climate variability, and I've spent a lot of time working on trying to improve our global ocean observing system for that purpose. So please forgive me, I'm going to make some comments about shelf observing, and I'm quite ignorant, so please forgive me if some of my comments are misinformed, but I have been looking at some of these issues. All right, so I'm going to just talk a bit about this from these observing challenges from the perspective of the global observing challenge, and then come in and look at what my view of what I see happening on the shelf and slopes. So we've seen in the last 20 years a true revolution in our ability to observe the global ocean, what I call the blue water ocean. This is the deep ocean, outside of the slopes into the abyssal areas. And this has been driven by many things. This is a multi-purpose observing system. It's not just addressing one or two questions. But I think we all know as scientists that given what's happening around us, we need to observe globally to understand what's happening locally and to attribute what we see locally. And so this is the current status of the global Argo array. I'm sure most of you know what this is. These are about 3,800 profilers profiling every 10 days. And just as one of the products of the global Argo array is this picture here, which shows you what we can just produce in real time every month. And this is the signature of warming in the upper ocean. So this is averaging right through the fleet. And you can see the climate change signal pops right out of that. And this is because, again, we're measuring globally, and the ocean's ability to move heat around from place to place gets averaged out. And you can also see at the surface there that the ups and downs associated with the El Nino Southern Oscillation are reversed at depth, and you integrate down through that, and the ocean heat content is just a staircase of ongoing warming. Okay, so there is no hiatus in warming when you look in this space. Okay, so I guess what I'm going to say is we need these for biogeochemistry, we need this for carbon, right? And we don't have it yet, for sure. The other thing I wanted to make a comment on is when we think about the observing challenge, we have to think of the whole integrated observing system, not just one network. And this is where asking questions about how the in-water observing pairs up with the satellite constellation of Earth observing sensors becomes really, really important. And so we need both of these things to get state estimates to understand what's happening in the system. And so I've just listed, you're all familiar with these, I've just listed some of the key ones there. These are all important for the deep ocean. These are just as important for the shelf and coastal ocean. And this is an integrated system, so those satellite systems can't really operate well or can't be used very well without the in-water system either. So Argo is particularly powerful when teamed up with the surface topography missions, the TOPEX Poseidon and other surface topography missions, because it extends that information from the surface down in depth and lets us start pulling apart, well, what is driving sea level rise? Is it fresh water? Is it heat? How deep does it go? Surface vector winds, very, very important. Good winds are important for the open ocean dynamics, just as important for shelf dynamics. These get calibrated using moored arrays. And then the satellite SST retrievals are highly dependent on our surface drifter network. So again, when we're thinking about building this observing system, we have to think about it in a really integrated sense and how things are codependent and can work together to be more powerful. So the main thing that Argo did was just sample when things were not being sampled. And it's really this autonomous technology that makes this much, much cheaper than in the past, where things were ship-based, that's driven this revolution. And so this is just a coverage plot of asking the question, which boxes have one profile per month every 2 by 2 degrees? And this is based on the archive that the French maintain at Coriolis, the Cora archive. So that's their best estimate of aggregating all the global data that they can find. And you can see there, the top left there is 2000, 2010, and 2019. So you can see the massive impact that Argo has taken in coverage there. So in 2000, we're looking at ship-based coverage. Then Argo starts to become implemented. There's still gaps, marginal seas. There's still political issues there. By 2019, we're starting to do better in the Antarctic sea ice area, and some of the marginal seas are starting to be filled in. Again, Argo also benefits and is very synergistic with, say, the ITPs that are starting to measure in the have been measuring in the Arctic, and the animal-borne sensors that get into the Antarctic and Arctic sea ice. So again, different platforms filling in gaps, a better system. So now I'm going to start looking at how we're doing in the shelf seas. So we've gone through also a profound change here, and my interpretation of this is, while through this use of mass autonomy, we are doing better in the deep ocean, I think on the shelves and slopes globally, we're doing worse. Okay, and so this is a question asking, what is that fraction of cells that have at least one profile per month globally, dyed by color? Oops. Stop button again. Yes. Okay. So so you can see, if you're interested in so this is the fraction of coverage as a function of time in the Cora database, and you can see that the fraction of shallow shells only starts out in the 2000s at around 5% or 10%, and it's actually going down. And then you can see the implementation of Argo. The deep ocean now is better sampled on average than our shelf seas and slopes. And my interpretation of this is that many nations are struggling to maintain those ship-based surveys that in the past made the shelves and slopes the data-rich part of the global ocean. That is now reversed. And it's a big problem for all the reasons we just heard about. So this is a big challenge we're facing here. This is just zooming into the Northeast, and here now I'm looking at what is in the National Data Center here, the NCEI archive, and I went back to the pre-COVID years, 2018-19, just to look at what is there. And this is for hydrography, temperature, and salinity. It's dyed by platform, so you can see those wonderful ship surveys that we just heard about in the blue dots. This is surveys, this is a profile location in a month, but for 2 years. And again, you can see the Argo fleet there operating in the offshore areas. And on the shelf, you can see the ship surveys, but there are large portions of the shelf, even in these recent years, where there is nothing. There is not a single profile, and this is just straight hydrography over the 2-year period for those months. And so here you see the challenge. And now let's ask the question about how are we doing for the most easily measured biogeochemical parameter. This is oxygen. Okay, so this is the challenge now we're facing. We have a really long way to go as far as increasing our ability to measure these fundamental biogeochemical parameters. I don't need to tell you that, but I just wanted to show you the stark reality. And so if you're like Charlie or others that are trying to build state estimates of these, the biogeochemical state of the ocean, this is what you've got to work with. This is a huge challenge. And so again, you see those wonderful ship surveys there that are collecting these observations. But apart from that, there are just massive, massive gaps. Currently, there's a sprinkling of biogeochemical floats in the offshore area, and I'll show you about the status of that network. But again, on the shelf, really very little data. Now, it could be that these data are not flowing to the archive, but that's a problem too, because these archives are the basis of our state estimates. And so if there's data that's not flowing into this archive, we have to fix that too. So you know these problems, right? And this is the challenges around this biogeochemical observing challenge. So for the blue water, I'm going to tell you a bit about Argo's proposals and hopes. But on the shelf, I think it's a fact we're going backwards in our sampling. Okay, and again, I think it's to do with just the difficulty of maintaining the ship-based surveys. In the offshore, the sampling and the proposals there is being enabled by a series of things. You all know what they are. Platform maturity, okay? Here we're talking about profiling floats and deep water glider technology. We're talking about sensor maturity. That represents a huge amount of work. We need low power and mass sensors stable. They need to be stable. And we also need these optical sensors now that are starting to give us insights into the base of the ecological system. And the other key ingredient I wanted to talk about was a clear design, a clear sampling plan. I think we have that for the broad-scale float-based mechanisms. I'll show you that in a minute. I'm not sure we have that for gliders or some of the other systems. So here is the proposal that Argo has for its future design. Currently, Argo still is largely a temperature salinity down to 2,000 meters. This is the one Argo design here. And basically, we want to convert 1,000 of these floats that we're operating, we hope to operate globally, to being biogeochemical floats, which means they have 6 additional parameters on them: nitrate, oxygen, pH, chlorophyll, CDOM, and irradiance, which ties us into some of the satellite systems. Okay, this is a proposal. This is being piloted, but it's not secure yet. So this, even in the blue water, this remains a really big challenge. So where are we as far as making this real? We have a fleet there. This is the pH fleet here, so you can see it's very, very, very sparse. There's only about 200 pH measuring floats out there at the moment. And so, the US has, through NSF, 2 funded kind of large arrays. These are research arrays. NOAA, who has been doing all the heavy lifting around core Argo and deep Argo, their investment in BGC remains low at the moment. And because this is a big funding challenge, right? The BGC, global BGC program requires 1 time what we are already spending on the core Argo program. Core Argo, deep Argo, BGC Argo together cost about the same as 1 sensor in space. Okay, so I think it's a great deal, but we need to convince governments that we need these because of these rapid changes that are going on and our need for insight into what's actually happening out there. Other countries are building capability to run this mission. We are dealing with some sensor supply issues, but I think these are all solvable problems. What we need at this point is basically convincing governments to invest. We've done all the hard work to prepare for this, and we're ready for the investment to scale up. But this is not in the bag yet. So this is the status that we're at for global biogeochemical measurements. Carly asked me to talk about a few ingredients of success in the Argo program, and I think this applies to the biogeochemical side of it for sure, and any other network. So one of the really important parts that made Argo really, really successful is our data system. And so it was designed to do 2 things. It was designed to drive data out very quickly, to make it available for operational centers, and it was designed to address the climate problem, which meant that we had to pay a lot of attention to data quality and accuracy. And so Argo invests about 30% of its budget in data management and getting the data up to that very high quality. We have very consistent and rich metadata and technical data, and all the data is freely available in real time, both to the operational centers and on the internet. And the other really important thing is we enforce very strict formats. So before your data turns up on the assembly center, it goes through a format checker. If you do something wrong or a field is missing, the file gets rejected. So there's gatekeepers as far as making our data very uniform and machine passable, and that drives up the utility of it. And the other key ingredient to success, I believe, is a very, very clear design and performance metrics. So Argo had a very simple design, and we've stuck with it over the years. Now the new design is more complex, but we can also write down performance metrics. But every day, every month at Ocean Ops, we can look at a coverage map on the top right. So that the dots there are from the original design document back in 1998, and the actual array looks a lot like that. We look at coverage maps that tell us how well we're doing against our target spatial coverage, and so we can look for places we need to target. The West Indian Ocean is one right now where ships have not been going due to COVID, so we're busy trying to find ways to get in there. And then we can look at time series of coverage over time, and so 50% is what we're shooting for globally. So we look at these every month to figure out how well are we doing, are we actually delivering data on the time and space scales that we promised. So I think this is very powerful in how you not just set the system up, but how you operate it. And so when I think about the shelf problem and the ship problem, gliders are an obvious potential solution here, and I know there are many people that have been operating gliders on the shelf. But when I looked really in the US system, there's only a few examples of very deliberate, sustained repeat sampling. And here are two. One is on the West Coast, those Calcoffee lines that we've heard about. And on the right is the glider operations that Robert Todd is doing in the Gulf Stream. These are very repeatable, sustained, deliberate sampling, very powerful. But you'll notice that most of the data they're collecting is not actually on the shelf. These are deep water gliders. They're looking at the slope boundary interaction. They're not contributing a lot to the actual shelf observations. But I think these programs show what can be done with the glider network. And so I guess when I look at this problem, and I am an outsider, I would be asking these questions, what would a backbone shelf observing system look like? Okay, and how would you inform that? I think you would inform that by all your knowledge of the system as people working in that space, but also the modelers that are ingesting this data to try and drive the accuracy or the errors down in their state estimates. Okay, so I think it's crucial to ask those questions. What is the target space and time sampling required, and how would you build a system to deliver that and then track how well you're doing? And then the question is, what biogeochemical and optical sensors should be carried by those? I think we know a lot of those, but there are really new, exciting, emergent systems on the horizon. And then I think a very powerful aspect of this is we would like this to be a seamless observing system. So a parameter you measure on the shelf should be have the same characteristics as the parameters that you're measuring in the deep water. And so as a user, those measurements should be seamless. So we need to be thinking about how they aggregate into the offshore observing system. And the boring work, but essential work of common standards, formats, real-time data sharing, delayed mode, high-quality data, I think these need to be put in place. And I'll just make a comment in recent work I'm doing in trying to, Argo's been operating for 20 years. We can now build meter-scale resolving climatologies, which, our models are now operating at a 10th degree, a 5th degree globally. Those models need really highly resolved data to challenge them. Because we've been doing Argo for 20 years, we've been sampling randomly, we're starting to resolve the mesoscale structure of the mean circulation. We need that for the shelf too. Just having a really good seasonal climatology is incredibly important. But when I tried to go for fine shelf data to add to what I'm doing, there's not a single website where, say, all the US glider data is available. You have to go to many. We need to fix that and make these data aggregated, easy to find, very easy, low bar for users to get hold of it. And so I think we all know what the future challenges are around biogeochemical sampling and getting it into the coast. I've mentioned some of these: high prices for sensors. There's some issues around dynamic errors in oxygen pH nitrate sensors that we as a community need to figure out. And then we need to figure out how to really exploit some of these optical sensors and the imaging sensors that are coming online. I've talked about the platforms there. If we go, I think autonomy and using gliders or floats is very cost effective, but there's still things we need to do as far as longevity, power efficiency, reliability. And then data communications, particularly around some of these new imaging systems, is going to be a challenge in the future. So I guess in summary, I'll say in the blue water, in the deep ocean, we've made a tremendous amount of progress in the last 20 years. I think we've been able to really exploit the synergies between satellite and in-situ systems. And the mass use of autonomy has really been the thing that's allowed us to do this and truly go global in an affordable way. But I think a clear design and sampling goal is really, really important in not just costing the system, but operating it. Scaling up to do global BGC coverage is immediate major challenge. I think we've done a lot of the capacity building, the platform and sensor work, but right now we just need governments to invest to make it happen. Once it starts to get scale and we deploy more and more things, we think that some of these issues around prices and availability with our manufacturers will go away. On the shelf and slope, I would say, even for hydrography, we might be going backwards. And so, you know, I think there's an urgency here in my mind, given the changes that we're seeing. And I suggest that there must be a more deliberate way that we can design a shelf observing system to underpin state estimate and to really come up with clear sampling goals to help us understand how well we're doing and how we're operating it. And then, you know, I'm sure you've talked about this a lot, but the data management system is absolutely vital if you're going to get value out of those assets. And so investing in that is going to be critical as well.
Yeah, let's take like one quick question while we're making the switch, and then the discussion session. There's a lot to unpack there. So, thank you very much, Susan. I think I saw Grace first there. So, Grace up there.
Thank you, Susan. I just wanted to address some of that. I don't know, for some reason, all of our glider tracks aren't showing up on your map. So something's broken there. We need to fix that. But in terms of your comment on data and like not being able to find glider data in one place, I know Ocean Gliders is trying to do that. It's the international glider component of GOOS, so that we've had a lot of discussions and trying to figure out how best to do that. So I just wanted to make that comment, but I would love to talk to you a little bit more after, because
yeah, sure. I mean, I know about that. I've been in rooms where that's been talked about for a long time. So I guess, you know, if you're starting new stuff, I would say you want the data system in place, or mostly in place, before stuff goes in the water. So we know that now, but easily said. But I think as a community, we tend to cut our budgets in data management. We don't invest enough, and that's on us, right? And so I think as a community, that 20, 30%, like, you know, you don't have time to like say how much you need, like, because you haven't done it before, but it's at that level. It's not a small amount of money. And so, you know, I think it's on us. We need to make sure that we invest to get the data out.
I'm confident Grace can solve it. Everybody else? Yep. Thanks again, Susan, and she'll be back for the discussion session. So, but now it is a pleasure to introduce Susanne Craig, who is going to talk to us about the advances on the observing from the remote side that may improve our capacity to understand coastal oceans. I could tell some jokes while they get that up, but that would be unwise. So. My kids just did give me a book of dad jokes for Father's Day, so I'm really hoping this comes up. I do not want to have to use them. the nosy pepper? Yeah. It's all up in your business? All right, it looks like we're good, so you guys are saved.
Hey, can everyone hear me? Yay. Okay, I just wanted to break the ice a little bit by showing you a pretty groovy little time lapse. This is our NASA's upcoming ocean color and atmospheric mission being built at Goddard Space Flight Center. This is OCI being put together, ocean color imager, by all of our groovy engineers. This is the thermal vac test, so it's all been assembled, it's been put together. It goes on a big dolly, they push it into this giant pressure cooker, and then they shake it really hard, and they break all the optics, and we all have nervous breakdowns, and then, yeah. So anyway, I just wanted to break the ice there, showing you some of the groovy work that goes on, and you can see, I always laugh because the engineers are really stoked to do this. They're all taking selfies as it's going into the vacuum chamber. Okay, so as Charlie said, my name is Susanne Craig. I want to talk about some aspects of remote sensing, particularly in this coastal zone that we're concerned about today. I want to talk both about the challenges and some of the solutions and opportunities that are available to us as a community. So some of you in this room are ocean color experts. Some of you might not be. Just to get us all on the same page, I thought I'd do a little ocean color primer, Ocean Color 101. When we refer to ocean color, what we're referring to is the following. We have a satellite that orbits the Earth. It collects contributions of radiance or scattered light that come both from the ocean surface, but also a really large part of that radiance comes from the atmosphere itself. And rather unfortunately for us as the ocean people, only about 10% maximum of the signal the satellite sees is actually from the ocean surface. So this is what we want, this is what we've got. How do we get to the water leaving component? Well, we've got to mathematically remove that atmospheric signal to derive the water leaving signal, which contains all of that biogeochemical information that I'm going to tell you all about today. So more on that later. So just a little bit more on ocean color. When we refer to ocean color, we're often referring to a quantity called remote sensing reflectance. You'll hear me use the two interchangeably. And ocean color is what we call an apparent optical property, which means it results from the interaction of the incident light field along with the optical properties of the water itself and the constituents in the water. And those constituents for our purposes are phytoplankton, non-algal particles, things like detritus, fecal pellets, go poops, Debbie, where is she? Suspended sediments, flocks, etc. And then we also have a colored dissolved organic matter, or CDOM for short. That's the colored part of the dissolved organic pool that we can quite conveniently detect from space. Okay, so my take-home message, just to drive it home, is that ocean color, of course, contains fundamental information on both the types and the concentrations of water constituents. Okay, so a little bit more on this primer thing, so we're all on the same page. How do we actually get that information from the remote sensing reflectance or ocean color signal? Well, this is actually real data. This is data collected when I ran a coastal observation program out of Halifax in Nova Scotia, the eastern coast of Canada. We start with our remote sensing reflectance. We then run a number of different approaches, different models of different flavors. They can be things like band ratio algorithms, where we compare the blue part of the spectrum to the green part of the spectrum, tells us something about how much chlorophyll is there. We can use what we call semi-analytical models, which are a combination of models and empirically derived constants. And then more recently, we've begun to use machine learning. Like many of us in the oceanographic field, we're seeing the power of machine learning. Okay, and what I'm just showing there is how a lot of the constituents absorb very strongly in the blue part of the spectrum. Water itself and phytoplankton also absorb in the red part of the spectrum. That means they remove photons. So a typical coastal reflectance signal has fewer photons in the blue and the red due to the absorption, and then a lot of reflectance in the green. Okay, so using these algorithms, we can derive both chlorophyll and these inherent optical properties, which act as very good biogeochemical proxies for biogeochemical processes, which are of climate relevance. Let me just show you how we use, typically I can use these types of proxies. I'm just showing a few examples here. This is one of my favorite all-time animations, I think. This is the very famous NASA Global Biosphere. It's a composite 20-year data set made up from the chlorophyll data product from Modus Aqua, CWIS, now deceased, and the VEERS satellites. We're showing both the terrestrial vegetation index, but importantly for us as oceanographers, you can really see that the pulsing of all of those global processes, including the northern spring bloom, northern hemisphere spring bloom, and the results of things like El Niño and La Niña. So you can really see the earth breathing. I love this animation. It's absolutely beautiful, and it's free for anyone to download by following the link. The other example I wanted to show you is, let me go back there, is using ocean color to detect and assess and give early warnings for harmful algal blooms. And this is just a great example here, the Cyanobacteria Assessment Network, or CYAN for short. It's a multi-agency initiative at the NASA end of things. My wonderful colleague, Bridget Seegers, heads up the NASA parts of the activities. And this is just a little example from one of Bridget's awesome presentations. If you ever get to see Bridget talk, go see her. She's a hoot, and she also gives free beer at her seminars. So, yeah, watch out for her. Just showing, one of their success stories where they were able to look at the succession and development of a harmful algal bloom in Utah Lake in the summer of 2017. Okay. Another example that I'm showing here is how we can use the satellite-derived absorption by CDOM signal to tell us something about the dissolved organic carbon pool in the Arctic. This is a very nice paper by Atsushi Matsuoko and colleagues, where they worked in the Arctic. They first of all established that there was a strong relationship between dissolved organic carbon and the absorption of CDOM at a blue wavelength. This was done in real water samples. They could then use that nice relationship to get absorption by CDOM from space, then converted into DOC. And here you can see the various distributions of DOC in the Kara Sea for different times of year in that Arctic study that they did as part of the Takovik set of activities. Finally, this is a set of examples of how you can use ocean color in inland waters. This is by my colleague Karen Binding, who's up in Canada, Environment Canada, where they actually found that when Lake Erie develops these harmful algal blooms, it's very strongly related to the total suspended particulate material load and the sediment transport. So they get a lot of transport and runoff from the land that initiates these blooms. And that's just showing a time series there of all the different blooms that take place in Lake Erie using one of the HAB algorithms. So let me talk a little bit now. I told you all about the wonderful things that ocean color can do, gives us these synoptic pictures, global coverage. But let's talk now a little bit about some of the challenges of using ocean color in the zones that we're interested in as coastal oceanographers. The heritage ocean color sensors, so things like Modus Aqua, which is currently still flying, and VEERS on the Suomi NTP platform, they have pretty large pixel sizes, large in the sense of the processes that we might be interested in the coast. Around a 1 kilometer squared pixel size when the sensors at nadir as it's passing over the target water body. Their global coverage frequencies are around 1 to 2 days. And of course, both that spatial and spectral set of characteristics are pretty mismatched with the scales of the coastal processes that we might be interested in. So that's one of the drawbacks, unfortunately. I'd also like to talk a little bit more about some more of the caveats involved in coastal ocean color by introducing this concept of optical complexity, whereby in the open ocean basins, the color of the ocean is essentially controlled by phytoplankton. Everything else, the CDOM, the suspended particulate, non-algal particulate material, they all move up and down with chlorophyll for the most part in a commensurate sense. So everything behaves well and co-varies together. As we move along that optical complexity continuum, moving from open ocean basins to shelf seas and then to these coastal estuaries and wetlands and inland waters, we get increasing optical complexity. And what I mean by that is that those other optically active constituents, i.e. the non-phytoplankton parts, they do not co-vary with the phytoplankton. They move independently. So that's rather unfortunate for us because it means lots of different things. Number one, we find that some of the assumptions in those models that I talked about, they break down because they rely on an assumption of everything co-varying together. So number one, that happens. I told you we needed to remove the effects of the atmosphere. That can actually be quite difficult to achieve in these optically complex waters for a number of different reasons that we don't need to go into right now. And we also have things like the adjacency effect, and that's an effect whereby when you have a land-water interface, the bright land pixels, the land's pretty bright radiometrically compared to the water, bleeds into the darker ocean pixels, and you get a kind of spectral contamination effect. So let me just focus in on that part there, that accurate atmospheric correction is pretty difficult to achieve. You don't need to look at this giant laundry list of an equation here, just these 2 points. This is what the satellite sees, okay? It's up there looking down at the ocean through that giant limb of atmosphere. This is what we want. We want that water-leaving signal that exits out the air-water interface and is scattered in the upward direction. These are all those fancy schmancy math and coefficients that we use to mathematically subtract the atmosphere. But as we move into those coastal waters, that can actually be quite difficult to achieve for lots of reasons that include things like the fact that the aerosol assemblage at the land-water interface actually becomes very complex and difficult to model accurately, and it becomes this dynamic mix of maritime and terrestrial aerosols and sea spray. So that's just one of the reasons that we have a lot of, bless you, that we get this, this challenge of atmospheric correction. Just to show you what that looks like in a spectral sense, what I'm showing you here are some CWIF spectra where atmospheric correction has gone a bit pear-shaped. I'm showing the pear-shaped spectra in the black, heavy black symbols. And this is where we see that the reflectance has actually become negative because we subtracted too much atmosphere. The model didn't accurately reflect what was actually happening with the atmosphere. Typically affects the blue end of the spectrum most strongly. Okay, and what does that look like when we try to make these nice images? This is just listed from a paper by Carswell et al. In 2017. These are coastal water bodies in Western North America. Just a number of different algorithms and atmospheric correction approaches. But what the thing to notice here is that they're getting, you know, nice kind of spatial distributions of chlorophyll. Could be real, could be not real for all the reasons I talked about. But you notice that there are these missing pixels all adjacent to the coast. That's approximately about 1 to 2 kilometers, a couple of pixels worth out from the coast. So we're missing all of that biogeochemical dynamic action when we flag those pixels for having failed atmospheric correction. Okay, those are some of the caveats. Let's not be too depressed about it because there are solutions. We just need to start to think a bit more creatively as a community. So what many folks in the community are starting to do now is use satellite sensors with higher spatial resolution. Some of these sensors might not be specifically manufactured for the ocean. They're multi-purpose, but they work in an engineering trade space whereby you get better spatial resolution, but you lose some of the fidelity in terms of the signal-to-noise ratio for the darker targets. However, they still work really rather well. And 3 examples that I've got up there in that table is the OLI on the Landsat 8 and 9 satellites, the MSI on the ESA Sentinel-2, and OLCI on Sentinel-3. You can see how much higher the spatial resolution is for these instruments. And you'll notice that the global coverage frequency, unlike our MODIS and VIIRS, it's not every 1 or 2 days, but rather it's you know, handfuls of days, even with a 2-satellite constellation, whereby you have out of phase satellites, sister satellites doing this so that you can increase the coverage time. So here's a really nice example by my colleague at NASA, Nima Palavan, and lots of colleagues there. And what Nima and colleagues did, they used a combination of Landsat 8, Sentinel-2, and Sentinel-3 to derive various water quality indices, which included chlorophyll A, total suspended sediment, and colored dissolved organic matter, so that colored part of the dissolved organic carbon pool. They used a machine learning approach. You've heard a lot of folks begin, especially Gillian McKinley at the beginning of this week's workshop, talked a lot about their developing machine learning approaches. The ocean color world is moving in that direction as well, but a bit more slowly. And the particular approach they used in this case was mixture density networks. You can see they get beautiful spatial resolution in a relatively small water body. This is the Potomac River going into the Chesapeake Bay around Maryland and Virginia. And they look great, but let's not go with the LPG model. Looks pretty good. Let's have a look at the actual error metrics. They did a really nice, very candid and thorough error analysis for all of those products. I'm just showing an example here. Lots of text, but things to take home are the measured value, i.e. measured values from water samples that were grabbed and analyzed in the lab is on the x-axis. The estimated values are from the various different models and satellites that they used. And the one-to-one line is this dashed line going up through the diagonal for each of the plots. This particular one is looking at error metrics for chlorophyll. It's a bit of a, all kudos to them. They've absolutely reported everything with utter candor. Yes, they get results. Yes, there are relationships, but there are biases. There are huge spreads, even in this log-log scale. The points are not homeoscedastic, or in other words, equally distributed around the one-to-one line. So we're still having challenges both in atmospherically correcting with these higher spatial resolution sensors, and because of that, having challenges in getting accurate estimates of the biogeochemical proxies. I'm now going to shamelessly toot my own horn and say that I've been thinking about this problem for a long time. Working in optically complex waters is my kind of thing. I love the complexity of it. I love the fact that there's so much dynamic biogeochemical and ecological information there, and it's where we as a species interact with the ocean. So just to give edited highlights from this, I can give a lot more detail, but this is more of an overview. Myself and a data science colleague, Dr. Erdem Karakoylu, who used to be a colleague with me at NASA GSFC, we developed this approach where we use Bayesian models, specifically Bayesian neural networks, to derive biogeochemical information from ocean color. It's just about to be pushed into the peer review system, but just so I could get a DOI, everyone get DOIs, put your stuff in preprints so you get DOIs. It's currently in the Earth Archive preprint ecosystem. You can find it there, or even just for searching in keywords. Key points to take home about this. We did not do atmospheric correction. We started with the signal right at the top of the atmosphere. We didn't try to be clever. We didn't try to model the atmosphere. Instead, what we did was we started off by doing a principal components analysis on that top of atmosphere spectra, which is actually quite featureless. It's like a monotonic decay with wavelengths. But when you do something as simple as a PCA analysis, what you're doing is looking for those dominant modes of variability, and lo and behold, that giant atmospheric signal that contributes about 90% of the first mode of variability, it pops out, and when you put it into your model as a predictor, your model says this contributes nothing to predicting the things I'm interested in. In our case, it was chlorophyll or other optical proxies for biogeochemical information. Because it's a Bayesian probabilistic framework, our uncertainties come for free. And this is the part that I derived the most pleasure from. This was a real 50-50 collaboration with the domain specialist, me, the ocean color phytoplankton person, and my data scientist colleague. So a lot of the time, people are resistant about data science and machine learning. They say it's a black box. No, no, no. Done effectively, As Galen explained to us earlier in the week, these are real collaborations between us with all of the domain specialism and knowledge of the systems, and then the data scientist helps us implement the most powerful machine learning data mining approaches. So hug your data scientists. I love my data scientists. Okay, more shameless tooting of my horn. Here are the results. This is a similar plot to the ones that we saw before for the error analyses, where we've got what we observed in situ, so real in situ samples, and what the model estimated for us. Just remember, Bayesian approaches give you a distribution of inferences or estimates. So what I'm showing are the mean of those distributions, just to get a single data point to show you this kind of one-to-one relationship. We do really well. We do much better than when we try to atmospherically correct. So just do it the easy way. Don't try and atmospherically correct in these optically complex waters. The nice thing that was gratifying is the blue wavelengths, which are like 411 and 443 nanometers. They actually behave very well. And in conventional approaches, those blue wavelengths are actually the most challenging to correct. You saw how they go negative when we use conventional approaches. Just to flog the horse a little bit deader, just comparing those same results, this time we're showing one of our off-the-shelf operational models. It's called the GIOP, which we run at NASA on a routine basis. The GIOP conventional model with atmospheric correction is in triangles. Our Bayesian neural network is in circles. And you see how non-homeoscedastic that is in a one-to-one sense, a lot of bias. So take-home message, this works. It's fairly easy to implement. We have the code shared in a GitHub repository. Happy to talk more at length about that with anyone who's interested. So take-home messages, the neural networks were able to accurately estimate these biogeochemical proxies from the top of the atmosphere. We didn't have to worry about atmospheric correction, or AKA our nemesis, particularly relevant for the coastal, inland, and optically complex waters that this session is about, okay? We get robust estimates of uncertainty. These are things we really want to know. We want to know the skill with which we're providing our end users knowledge or data products. Resistant to overfitting. The nature of our type of work is we have sparse labeled data, makes our models pretty sensitive to overfitting. These types of approaches can circumvent those statistical caveats. Okay, last few minutes, I just want to talk about upcoming missions and how they may be of interest to this community of people. First of all, I want to talk about PACE, which is short for Plankton, Aerosol, Clouds, and Ocean Ecosystem. It's the new NASA Ocean Color and Atmospheric mission. You don't need to read all this blurb. This is an agency standard chart. Pack in as much useless information as possible, but the animation is very beautiful. Behold, we have a great AV set of folks that do these lovely things for us. Okay, take-home messages for us. PACE is intended to support ocean biology, ecology, and biogeochemistry, also to facilitate the investigation of atmospheric aerosols, clouds, and land. So that's important for us as a community because we're interested in all of those intersections. Okay, another thing to take note of, we're shooting for a January 24 launch. We've been impacted by COVID like the rest of the world, and that launch is delayed. Here's some more information about it. It's a hyperspectral mission, which means instead of having wide waveband chunks to detect the ocean color, we have a lot of spectral resolution. We will sample to 5 nanometer resolution, but the hardware actually gives us the capability to measure 2.5 nanometer res. And the thing that I want to kind of impart here is that by having this hyperspectral capability, the coverage at a global level is going to provide us with unprecedented insight into phytoplankton community composition. We've spent a long time in this community talking about how hyperspectral data can give us a lot more information into the types and groups of phytoplankton that are present. We also have these polarimeters on here. They're intended to look at the atmosphere, but as a bonus, the polarimeters also, the polarization state of the ocean surface can also tell us something about the water constituents. So it's a win-win for the oceanographers and the atmospheric scientists, okay? And that's just a little bit about the synergy. We're doing aerosol characterization. Remember, the ocean is a source of biogenic secondary organic aerosols, so that's going to provide a lot of insight into that as well. Okay, caveat about PACE. It's a wonderful, wonderful mission. We're super excited about it. I'm one of the leads on it. Ivana Stefanich is here. She's another one of the science leads at the NASA end. This is the time and length scale that we are interested in. PACE is here. We're kind of missing coast again. Not to say we can't use it in larger inland and coastal water bodies, but we're not down to tens of meters resolution. Okay, just a little bit of an infomercial. As part of the PACE mission, we have a dedicated applications team. Erin Urquhart and Natasha Sadoff are the two wonderful folks that run that. Maria Georgiou is also a part of the applications team at the HQ end. Maria is here today. They have an excellent early adopters program intended to prime future community use of PACE data. They're establishing a community of practice. They are really interested in hearing from any of you in this community who think they might have an interest in PACE data. The idea being that we tailor a lot of our knowledge and data products to the needs of folks that will use it. Okay, and finally, just to finish off, another exciting development is the award to Joe Salisbury and colleagues at UNH of the GLIMMER project. It's the Geosynchronous Literal Imaging and Monitoring Radiometer. Deputy PI is Antonio Menino. Again, Applied Science Lead is the wonderful Maria Georgiou, who's here. Please ask her lots of questions if you have it. This is a geostationary proof of concept instrument, which means it will focus, it will be in synchronous orbit as the Earth rotates, and it will focus on the same areas of the Earth. Let me just start the animation. Here are the areas of regard: Gulf of Mexico, East Coast, West Coast, Amazon River, and then it can be targeted to do as needed characterization of phenomena such as harmful algal blooms. Just a little bit about it. Again, it's a hyperspectral mission. It has high temporal resolution. Ultimately, we're hoping 2 times a day for certain regions, 3 times a day for HABs, possibly early scans for the Gulf of Mexico to really get at those tidal processes. Okay, and again, here is this spatial timescale plot. These are the scales that GLIMMER is intended to investigate. So much smaller spatial scales, much shorter temporal scales, really allowing us to look at a lot of those rapid sub-mesoscale processes in the coastal ocean. And then my little soapbox, you've heard me ask questions about it all week. UAVs, unmanned aerial vehicles, are a really under-tapped utility for us. They capture scales that we're interested in. They're responsive, they're inexpensive, but it just requires a lot of coordination with our colleagues and ground teams. The take-home message is that all of these other types of suborbital ocean color missions address the subpixel variability, and they fill those satellite spatial and temporal gaps that I've spoken about here. And as Susan just told us, autonomous measurements really are the future. Along with mixotrophy, also autonomous measurements are the future, especially for ocean color in concert with programs like Argo. Okay, yeah, just a little bit about data. We really, everyone funded by NASA has to put all of their data into the CBAS repository. It's a forward-facing, public, freely available database. NASA's also pushing this idea towards open science. Check out the TOPS TOPS program. And just a thought that I want to leave us with, something near and dear to my heart, is this idea of how data science and open science principles can be a very tangible and achievable means to decolonize and democratize science. And I invite you to look at these links here, a commentary in Nature that explores the fair care principles. I'm just going to leave you with more crazy time lapses from our trusty engineers. Thank you very much.
So maybe we can take one quick question, and then we'll have our break and then come back to go underneath the waves. Does anyone have a quick one before coffee? Anyone brave enough to stand between the group and coffee? Yes.
Thank you. This will be really quick. I apologize if I missed the detail in your talk. What's the expected lifetime for PACE?
Expected lifetime is, we have 10 years of fuel. You know, pretty much guaranteed, I think, 3 to 5 years. But remember that CWIS and MODIS actually ran for 20+ years. So those are very conservative estimates. So yeah, that's the kind of time frame that we put on paper, but then last for longer. Yeah.
Let's thank our speakers again and save more questions for everybody for the discussion. So as we said this morning, now we're going to start dipping under the waves here. That series of 3 15-minute talks that combined will hopefully give us a sense of the in-situ observing space. Adrienne is going to start us off. Adrienne Sutton is a research oceanographer from the Pacific Marine Environmental Laboratory. And then she's going to be followed by Grace, going further under the waves, and then Alec with partnerships with commercial fisheries to make observations. So are you all set to go, Adrienne?
I think so, yeah. I had to do some video maneuvering, but I have one video I think I can show. So I'll just start off to save a little time. I'll talk about autonomous surface platforms for the coastal ocean. And this is stuff I've learned from a lot of smart people that are here on this slide. So there's a lot of really great people I get to work with and learn from every day. I know what the second slide is. So the first part of my talk, I'm going to talk, you're going to hear me repeating a lot of what Susan said. And that's no mistake because we've worked for, 6 years together on designing the next generation of the Tropical Pacific Observing System. And I think we both have like honorary degrees in the framework for ocean observing now. But at least that's the way my brain works. So yeah, you'll hear a lot of repeats on that. Thank you. And I'm going to walk through a case study in that first half of the talk that's around asking this question, which I get asked a lot, and I can't answer. So we'll walk through a case study. And then the last half of the talk, I'm just going to do a quick tour around other types of surface autonomous observing technologies, but also some near-surface stuff, too. I'm cheating, going a little into the subsurface. So this is an example from Atlantos. That works through the process of building a fit-for-purpose observing system. So you first set your observing objectives and requirements, right, based on your research questions. You then can identify the phenomena and ocean variables, or EOVs, that you need to measure to meet those objectives. And only after you've done that can you start to set your observing strategies and figure out what technologies are going to work for you. And as Susan said, before you get those technologies in the water, come up with your data management plan. Whether that's distributing data and data products to a wider community, or whether that's using the data internally, like the really great example that we heard from the exports field campaign. While they were at sea, they didn't just figure out how to integrate all that data at sea. They did that well before they got out there. They did that during the proposal process, is my guess, too. So as a case study, the objectives of our buoy network that I manage at PMEL is to characterize the progression of ocean acidification and CO2 uptake. Another objective is for some of these sites to serve as technology testbeds, because technology is constantly evolving and we need sites where we can test these technologies. And a major focus of ours is to make the data publicly available to support all kinds of stuff, process studies, models, climate assessments. So those requirements led to the development and use of the MAP CO2 system that I talked about on Monday, which makes the climate quality measurements of air CO2 that we need. And the additional measurements that we make are really to contribute to our understanding of the long-term change in the context of natural variability of the broader biogeochemistry. And then in terms of buoys, we use a variety of technologies. We can't afford the maintenance and all the ship time necessary to support these measurements at all of these locations. So this network is partially opportunistic, where we're deploying our sensors on other people's buoys, like the WHOI buoy that's at the Hawaii Ocean Time Series Station. You know, we don't maintain that buoy. We're leveraging off of our partners' funding to maintain that. But there are some areas that are a priority for ocean acidification where there are not assets, like in American Samoa, where we have a buoy at a coral site. And we use these smaller buoys that are modeled after the DART tsunami buoys that were developed at PMEL. And they're pretty lightweight. They can fit on a wooden pallet and can be towed to a coral reef or deployed from a really small boat like the one that you see there. We dedicate 20% of our budget for data quality control and management. And that includes funding the expertise that we need to make the constant technology upgrades to not only keep up with obsolete technology, but also to keep up with the changing needs of the stakeholders, because the stakeholders aren't static either. And I had to work hard for that 20%. And you have to build this in early on, or else it's just going to overwhelm you. Because we have that funding, we share real-time data for viewing with our partners at the IUS regional associations, like the example here with NANUS, and then we archive the data at NCEI. But we also develop data products and tools. We have a tool on our website here shown where you can explore how local conditions surpass a certain threshold, like a shellfish larvae threshold. So you can control this threshold bar, and it shows you how often conditions fall below it within each monthly climatology at each location. This is used a lot by educators. And then we have a time series data product that we make data easily accessible and available in several different formats, because we have stakeholders that are from the range of high schoolers doing a school project to biogeochemical modelers who want a machine readable format. And our next challenge is making real-time data available for data assimilation models. And we do that because we have this sustained funding to do it. Okay, so that's a quick case study. And so I just want to take on a quick technology tour. Here's a list of the GOOS EOVs for biogeochemistry, biology, and ecosystems. And here's a list of the different types of sensors that can be deployed on many autonomous and near surface platforms in the coastal ocean. You heard a lot about optical property or optical proxies, acoustics, genomics earlier in earlier this week, and so the experts are here on all of these sensors. As you move into the subsurface, the payload available on most autonomous platforms starts to decrease. So you run into limitations for sensors. Sophie Chu led some work a few years ago to test a small, low-powered carbon sensor on a trawler that's pictured here in the middle. And that trawler moves up a mooring line using wave energy and then steadily falls, taking a profile. And what we found was that at this location, in this configuration, we could predict ocean carbon chemistry using temperature, salinity, and oxygen at a lower uncertainty than by using that prototype carbon sensor. So the newest, fanciest thing is not always the best fit. Where you know, since we have a sustained observing program, we also have to think about sensor robustness, ease of use, maintenance cost. And so all of that kind of goes into our, you know, algorithm for figuring this stuff out. So this may be one of the approaches that we use in the subsurface at our sites. Here's another moored profiler from McLean, which I believe is just down the road in Falmouth. So these have a larger payload than the Prowler, so you can deploy larger sensors on it, like nitrate sensors. This diagram is from Nemo off the U.S. Northwest coast, where there are several observing assets, including the subsurface buoy that has that profiler, as well as the surface expression that has the CO2 and ocean acidification measurements that we collect. So back to USVs. I talked about the sail drone and the wave glider earlier this week. Most of these other USVs are in earlier stages of integrating oceanographic sensors. Many of them are looking for partners to help them do that, if anyone's interested. These mostly operate by using solar-powered motors or by harnessing harnessing wind or wave power to move. They have a large payload, and their navigation systems and sensors are typically powered by solar also, and that's intended to be, intended to allow them to be long duration. Although this is the surface, so there's biofouling, and that's typically the limitation for these vehicles. I think they really excel in adaptive sampling. You're communicating with these all the time. You're getting data back. You cross a frontal zone. Whoa, that was cool. Let's go back to that frontal zone and start mapping it. That's where they really excel. Some of these platforms you can purchase. Others have a business model where you buy data or see days, like the sail drone. I don't have sail drones at our lab. We buy days on these things. Someone mentioned in the breakout reports earlier this week how new technologies are really great until they languish in the lab when you've lost funding or the technology becomes obsolete. That's not an issue in the data buy model. There are other pros and cons of both methods, and we can talk more about those. Let's see, the USV that's like getting some air at the top here, it's not an aerial US or whatever, but it's like surfing the waves or something. It does really great in the near shore, and it's targeting the surf zone. Like it can measure in the surf zone, which is pretty amazing. X-Ocean here on the bottom, they're really targeting defense and oil and gas, but they have done some genomics work and some fishery surveying work. And then another cool thing, Ocean Arrow, it has this sail that can go up and down. And when it goes down, the whole vehicle can then go subsurface. So there's a whole variety of capabilities here. There's a lot more of these every day. Here are 3 of the USVs that have invested enough in ocean science applications that they promote on their websites, you know, what sensors they integrate. So they can all measure a variety of EOVs. The Open Ocean Robotics USV that was getting air in that other slide has done some projects showing hydrophones in the nearshore coastal region. And in addition to the sail drone CO2 work that I talked about on Monday, sail drones have also been used for fishery surveys and marine mammal tracking along the West Coast and in Alaska. Here are some other emerging surface and near surface platforms. Drifting buoys have been around for a while, primarily measuring physical measurements, but there's been some recent work using them for coastal acoustics. But longevity of the sensors and biofouling is an issue for those, so that's a challenge. Low cost, easy to use mini moorings are being used. And MBARI has been working on floats that can be used in nearshore coastal environments too. So they're all emerging. There are more. It's a quick tour. So here's where I'm going to try and show you a video. They are not working from the PowerPoint, but I'll show you basically one video. I'll describe the others. These applications that you'll see for aerial drones may not be directly applicable to the kind of observing that we're talking about, but this is an emerging area, and I'm sure someone in this room can think of how we might use one of these for the kind of observing we want to do. Here's a drone that just a couple months ago was the first aerial drone to tag a whale. And look for this online. The sound is amazing. The sound is so amazing. You hear this like as it sucks onto the whale. Yeah, I mean, and this is really important stuff because right now we tag whales from a boat, which is really unsafe for the whale and unsafe for the human with a long thing trying to tag the whale. I mean, so I just think that is just so cool. And then this other video that I'm not going to show you, I don't have enough time. There's another aerial drone out there that has floats on it, and you can take the aerial drone, land it in the water. It then releases underwater autonomous vehicle that can take images below it. So there's some really crazy stuff out there. So I think we have a lot of opportunities. Surface platforms have a lot of capacity combined with all the sensors that we have now leads to a lot of really cool work. Cool work that's compelling, that we can sell. You know, we just have to sell it. But there are challenges. The ocean observing is a small market, right? And technology development is slow. Data integration and dissemination of products to key stakeholders is a really big job. We usually underappreciate that. We also underappreciate and underfund the fact that ocean networks and systems need constant technology refresh. So these are all just things to keep in mind. And I'll end there. Thanks.
Okay, so why don't we do one quick question while we bring Grace up? Whoever Drew saw first.
Adrienne, I know that you know that one of the challenges there on your slide is that the market for ocean observing is small. But I know that there's increasing demand from private industry and especially the insurance industry that is interested in changing that. And I'm just wondering if you want to talk a little bit about whether or not you expect that to change or grow, or if you think that's a pipe dream. I know it's an opinion question, but.
I mean, I think it has to grow. Climate change reality is hitting insurance companies, and they know that. You know, I know that there's, I mean, the ski industry in the U.S. West is now like hiring climatologists. You know, so they're going to be reaching out for us. The thing that I've learned from working with industry is that they move really fast. And we go at a different pace, and we go at a different pace for a reason, because we're deliberate and we want to make sure that we're doing good work. And, you know, finding the right industry partnership and aligning the cultures is really hard, but it's doable.
I'd also say that, you know, Jon mentioned that the numbers in fisheries are measured in the B's, not the M's, right? The billions, not the millions. So there's an industry there that's very small. So Jon said that was a very small percentage of the ocean economy. So maybe there's some hay to be had there. But let's move on to Grace. Thanks. Why don't we thank Adrienne again? And now Grace Saba is going to talk to us about eco-gliders.
Okay, thanks for having me. The ocean is changing. That's kind of the motivation of why I think a lot of us are here, and we do the research that we do. So I'm not going to like go explain this figure. But I think it really is the emphasis of a lot of technological advancements and research, but also technological advancements over the past decade or so. But we're also changing the way we're using the ocean, and I'm speaking very biased. I'm in the Mid-Atlantic right now. There's a lot of offshore wind development going on, and there's a lot of discussion on how we're going to observe our oceans when we have all these platforms in the water. So I'll talk a little bit about that today. So we kind of are familiar with the traditional biogeochemical and ecosystem monitoring platforms we have right now for coastal systems. I'm not going to go into detail. You've heard a lot about satellites. You've heard a lot about moorings and some surface vehicles Adrienne just talked about as well. We have a very traditional vessel-based sampling programs in the global ocean as well. And they all have their advantages and disadvantages. The same thing with gliders, which I'm going to talk about in a second. But the gliders, what we can do with the gliders, and hopefully it'll play this video. Excellent. So gliders are buoyancy-controlled platforms where that means that they are low power, and so they can have high endurance in the ocean when they're sampling. And so basically, they'll take water in at the nose cone, change your pitch battery, and go descend down the water column. They can detect the bottom, and so then they'll push the water back in. Push it out, and then they're going to ascend. And then once they get to the surface, we have Iridium and GPS, so we can talk to the glider. We can transmit data back. So you're getting data in near real time. And these gliders can be out for weeks at a time, sometimes months at a time, depending on what battery type you're using. Similar to what Adrienne mentioned just now, biofouling is probably the biggest challenge with the gliders. And we're getting high resolution sampling. And there's 3 different gliders up here. These are the 3 main coastal and open ocean gliders that we've been using. I focus on the top one, which are Slocum gliders made by Teledyne Webb right here in Falmouth. They're very good for shallow near-shore systems. So those are the ones I'm going to be talking mostly about today. And so we can go through, look at the vessel-based kind of vertical resolution here in this image, and get to glider-based resolution, which is very high resolution. It allows us to see, different water mass properties and things like that over time, but it's a good vertical resolution over time and space. And so we can get sustained operations with the gliders because we can put them out, bring them back in, put them back out, and they're out for weeks and months at a time. We can put them out in hazardous conditions. We have a whole storm glider program at Rutgers to help improve hurricane intensity forecasts, things like that. There's been a lot of discussion on loss of costly ship time and this increased need for autonomous platforms, and gliders kind of help fill that gap. And then kind of navigating the wind farms, having an autonomous platform going through the individual turbines. So we have a lot of different sensors that we can put on a glider. I have a list of them here. It's a growing list of sensors. There's a lot of development in this area. Some are commercially available, some are still in development, and one of those sensors I'll be talking about today is one of those. But anyway, we can get a large range of physical, biological, and chemical parameters now using these profiling systems. So what I really want to get into today is some applications that we've been using in our group at Rutgers, and a lot of other groups are using worldwide. The first one is looking at spatial dynamics of carbonate chemistry using gliders. We have very dynamic coastal systems, as we all know. There's a lot of different drivers that can change the carbonate chemistry, either exacerbate ocean acidification or actually alleviate ocean acidification in some cases. And at the very end of my talk, I'll just give some examples of how we're going to start using gliders for the baseline monitoring research to support the offshore wind planning process. So we integrated an ISFET-based pH sensor into glider. This was funded by NSF OTEC program. It's integrated, it's coupled with a CTD, so we're getting temperature and salinity at the same time. Yes, we have named her Foxy Lady. And it's integrated into the payload bay with a lot of other sensors. We have optics, puck, and air optode for dissolved oxygen, so we're getting a whole suite of biological, chemical, and physical measurements. Yui Takeshita has now a development working on the spray glider, putting this similar pH sensor into the glider, and that's being tested out in the California current. So this work was really championed by Liza Wright-Fairbanks, my graduate student who finished early this year. So we're doing all these field testing with the pH sensor. We've been running seasonal deployments now since about 2018. And these are the types of data that we're able to get now. So this is aragonite saturation state, which is not pH, but we're using the pH data measured from the glider. We're using total alkalinity estimated from our glider-based salinity measurements to then estimate aragonite saturation state, and finally kind of see a seasonal signal in the mid-Atlantic bight. And you can see well mixed in the winter. We're getting stratification starting in the spring. We're seeing some freshwater influx that lowers aragonite saturation state in the near shore. And then we're seeing in the summer, we get this kind of low signal in the bottom waters in the cold pool. And that's, we're trying to fly these gliders into important commercial habitats to kind of link the biology and the chemistry. And in the fall, we see overturn where we get this influence of Gulf Stream slope water coming on to the shelf that increases saturation state. So we're able to start seeing these seasonal signals in high resolution with the gliders. We're also able to now see event-based impacts to carbonate chemistry. And this is one example I wanted to just quickly show, that we had a warm core ring sitting off the shelf for most of the summer last year. You can see it in the satellite image here. And so we wanted to know how that impacted carbonate chemistry, and we had our glider out both years during the summer. And in 2019, this is kind of our typical kind of cross-shelf section, and this is temperature showing this cold pool that sits at the bottom of the mid-Atlantic bight. It has a pretty large spatial extent horizontally and a high volume along the shelf. In 2021, when we had the warm core ring, it pushed this warm, salty Gulf Stream influenced water onto the shelf, onto the outer shelf, and it dramatically minimized the cold pool that summer during that time period, and also increased temperatures on the outer shelf, temperatures at which we don't typically see sea scallops spawning. So we were thinking about how that might impact recruitment of sea scallops. But the carbonate chemistry, a very similar pattern, where we're seeing this kind of high aragonite saturation state water getting pushed onto the outer shelf. So that's kind of good news in terms of alleviating ocean acidification. But then we have to start thinking in terms of if, you know, how are organisms switching between different stressors. So we have expanded this, we have expanded these programs now thanks to funding from the NOAA Ocean Acidification Program. We've kind of expanded this regionally. We're still conducting seasonal glider deployments to look at the carbonate chemistry, and it's now in the Mid-Atlantic bight and expanded into the Gulf of Maine. And we have an upcoming project funded by the Alaska Ocean Observing System to deploy the pH glider in the southwest Gulf of Alaska, in collaboration with Jessica, who's here. And that was, again, one of those things where they lost ship time, unfortunately, and didn't have their last ECOA cruise. So but then it's been delayed for COVID and everything else. But we're getting it out there. It's going July, next month. So that's kind of the ocean acidification application, very specific application that we've been using for ocean health in the Mid-Atlantic and now Maine. But there's a lot of offshore wind development off the coast of the Mid-Atlantic. And this is kind of these are in the orange, you can see these are the kind of the lease sites planned. It's a lot of space, a lot of area in these very high fisheries dense locations where we have a lot of these historical surveys going through. And so we're trying to figure out how we're going to sample when these turbines come in. But also there's a lot of push to kind of figure out what is the baseline, right? And I mean, how do you estimate what a baseline is? But there's a lot of push to do a lot of baseline monitoring right now for these lease sites. So that's what we've been doing off the coast of New Jersey. There's a project led by Josh Cohut at Rutgers where they've put these passive acoustic sensors, the DMON sensor developed by Mark at WHOI here, that's going on a glider and for monitoring whale presence and detection. Here's the red dots here along the glider tracker where we've detected the North Atlantic right whale. So we're starting to monitor where the whales are at different times of the year. We also have a newly funded multi-year fisheries baseline project funded by Ørsted, one of the developers, and we're doing very traditional extractive techniques, but we're also implementing gliders to start comparing glider-based measurements versus the traditional extractive techniques, so things like fisheries biomass. So we're using gliders to, with our traditional oceanographic sensors on there with acoustics. So we've added active acoustics, and we have our gliders with passive acoustics as well. And we're really just trying to start testing the potential for those gliders with the active acoustics for measuring things like fish and zooplankton biomass to augment or replace traditional vessel-based efforts, which have been successfully done in the Antarctic now for the krill, the Kamlar krill assessment. So we're just trying to see how well gliders can do this. And then now we have a state project funded by the state of New Jersey, again, to look at these kind of baseline measurements in these offshore wind lease areas. And then to provide, you know, they're obviously very interested in environmental change, so they want to try to start a glider-based seasonal program that's going to continue through the years, we hope at least. And really, this is, the image here is showing a paired glider deployment. It's our first one we've ever done in terms of looking at full ecosystem. And these gliders have physics, they have pH. We're going to have, they have the passive and the active acoustics. We have to put them on two gliders because there's so many sensors. And we ran our first paired deployment in just one wind lease site. And we're able to kind of start thinking about how we're going to use those data to see if we can, how are prey and predators co-located? How is that dictated by drivers such as frontal systems, so we can get from our physical oceanography measurements? How are chemical and biological, how are they co-located? So we can start thinking about that in terms of research. We're going to have a ton of data to mine from all of these baseline measurements that are being funded by not only the state, but the private industry for the offshore wind. Very excited. The state project is going to run down the entire, from Sandy Hook, New Jersey, right at the Hudson Canyon, going all the way down to South Jersey. This is just one small track for a deployment we just did. So gliders are now ever present in our global ocean observing efforts. Talk to Susan, we got to figure out why they're not showing up. But we do have a lot of shelf, glider-based shelf deployments. Here's some tracks showing how they are globally. And these gliders now, we're using more gliders, but the sensors are being developed more and more. And so we're able to start adding those biogeochemical sensors around the world in these shelf coastal systems that are difficult to get at with some of like the profiling Argo floats that we've talked a lot about this week. And that's all I have, and I hope I'm not too far over. Oh, I have time! I have time. This was Rutgers' 500th glider deployment. We celebrated took a class out on the boat. And
I don't think I've ever heard a talk that showed more and then ended with, that's all I have. Pretty amazing. Quick question for Grace. We probably have time for one or two, and maybe we can get Alec set up too.
Hi, Grace. It's Andrea Fossbender, NOAA PMEL.
Oh, there.
Great talk. I think you might have said this and I missed it, so I apologize. But do your gliders have the active and passive acoustics with the pH and oxygen packages?
Yes. So the active acoustics can have the pH, but the passive acoustics has the oxygen, and it's interference issues with the sound. So that's why we have the paired gliders, because we can't put all the sensors onto one. But yeah, when they're flying in the paired mode that we're starting to do now, they'll have all of those parameters, and you can see the two tracks. We're pretty good at keeping them right next to each other.
Very exciting.
Yeah, it was really cool to see that.
Wilf Gardner, Texas A&M. A very interesting talk. You mentioned you listed the instruments or sensors. One of them said particle flux. that a new sensor, or are you really referring to optically measured and estimated particle concentrations?
Yeah, that's a good question. So there is a sensor called the LIST sensor. It's an imaging sensor that can measure particles, but that's not measuring flux. I know Felipa is here. So Felipa Carvalho has been working with Stephanie Henson's group and regarding the particle flux, and they're using optical measurements to measure that particle flux. Don't ask me what those algorithms are. I'm very interested in learning how to do that myself. But maybe Felipa can actually. Okay.
Yeah, we just
Sorry, I
had
put you on the spot.
I'm sorry. We had one deployment where we had the list with the optical backscattering, which is what you usually use to look at it. So we're hoping to get a better understanding by pairing the two instruments together. The problem is the LIST sensor, like Grace said, is mostly used for sediment, so big particles. So it's kind of a wild guess. So hoping to deploy it in open ocean and still see the particles. We're hoping. I'm going.
Thanks, Felipa.
Great. So let's thank Grace again for a great talk. And now it's a pleasure to introduce Alec Wong, who we first met yesterday. But we'll now be talking about a different project of building a cost-effective coastal biogeochemical observing network in collaboration with commercial fishing communities.
Thank you, Sean. Thanks for the great opportunity. This is what I changed my hat to sensor developer. So we're going to look at the coastal observing a little bit different. So this in this case, we'll see how the community-based approach may help us to do a little bit better. This is just a starting stage of this idea. So we try to get something going. We applied OCB scoping workshop. So we got a little bit of fun to get a community together. So maybe down later this year or early next year, we're going to have scoping workshop. So anyone interested, drop me an email, talk to me. I'll be very happy to get you involved. So this is the signal we, typical observe along the coast, right? So on the left is coastal time series at Pocasset River. It's a fresh tidal marsh river system, and at the mouth of it, we have a time series DAC sensor. That's our channelized optical system, the second version of it. You can see the incredible up and downs, the daily cycle tidal export from the wetland, along with the dissolved oxygen. So that's a very, very high frequency measurement. So we call this kind of signal a weather signal. Okay. So and on the right is machine learning model output, seasonality or climatology, seasonality of the northeast shelf, carbon parameters, DIC, alkalinity, pH. Sorry, I should get the bottom figure. This is the surface. The bottom is just more as dynamic as the surface. So this is the kind of signal we see, and that's the challenge. What do we have? So kind of summarize what do we have. So for example, if I'm interested in PCO2 sustained PCO2 measurement along coast, this is the number of the NOAA PMEL mass CO2 stations. Okay, I may miss a few, but you get a sense. Okay, and on the right you see 30 years, 3 decades of water column bottle measurement of carbon parameters. Starting from the early 1990s. Okay, so there's a little bit better coverage in the summer, but not much in the winter. The other two kind of in between. So as a comparison, this is the weather station map. in the United States and Canada, basically North America. And you can buy, portable weather station devices from, from places like Amazon, okay, a few $100s. So this is kind of the community-based approach, and then we all know that the weather forecast now is much better. So getting this kind of coverage is incredible useful. So the last year, this is an ocean shot call. So we put in this little concept. Why don't we put cost-effective or low-cost sensor on existing professional networks that people already talk a lot? In addition to that, maybe we can do adding commercial-based sensor networks. There's commercial underway systems on commercial ships. This is already going for decades, right? So I'm going to focus a little bit on the fishing vessels. So there are sailing boats, recreation activity, even marine animals. If we can deploy low-cost sensors, and we can significantly increase the coverage of it. And that's a kind of the first step. So we proposed this idea to establish a community-based, a fishery community-based low-cost carbon sensor or BGC sensor network in the Northeast. So on the left, the goal is, which I listed here, the concept, kind of the framework of it is in a figure and on the left. So the sensor can be deployed on the fishing gears, like the lobster cages, the trawler on the deployment, and then you can get full water column coverage as well as a near bottom time series. So on the left, you can see a picture that the current fishermen deploy a CTD on the fishing vessel. So once the sensor being bring up to the boat, then it can have automatically Wi-Fi communication with ship computer, download the data, and further transmit it to land-based server or cloud. So there's many advantages for this kind of approach with the fishing activities. Ship opportunities, you can have the full water column coverage. You can have the high resolution repeated coverage in the water column, and especially for the undersampled area. And there's the fishermen can directly use your data for fishing operation and resource management. So the fishermen already know this by deploying physical sensors. So they very much want to do this approach. So we started get a little seed money to develop a low-cost pH sensor. So that is underway. We need the sensors. So this is the review we did back in 2019 for Ocean Observe 2019. So kind of summarize what do we have. So on the left, a few low-cost sensors, pH, DO, nutrients, lab on the chip. And then on the right is to kind of summarize the cost and the readiness level. So we call it low cost. So the definition of the low cost is at least several-fold cheaper than the existing commercial sensor. But you can see most of those low-cost sensors is still in prototype stage. But the methodology usually is robust enough, so we need to give a little bit push, so make it more ready to be deployed in community-based network. So the network, as I mentioned, we're going to build this network on existing, decade-long existing programs, fishery-based management program. So on the upper left, you can see the fishery-based program in the Northeast water. The coverage is pretty good, pretty much cover the entire shelf area. Lower left is the computer app that NOAA Northeast Fishery Study Fleet developed for the fish captain to visualize the data they collect. You know, the fisherman is pretty happy with this kind of engagement, so they can see what they get, and that can be developer used for their operation. The middle part is more of the scientific funding. This is from EMODE program run by Jim Manning at NOAA East Fishery. This is the data show 20 years temperature, seasonal temperature at a fishing site of New Hampshire at about 36 meters. So you can see incredible, you know, seasonal variability and the trend over the last some years, the warming trend at the site. Okay, this is near the bottom. So on the right, this is the CFRF Shelf Research Fleet Program, collecting salinity profiles of the shelf area here. So the zone 4 near the kind of outer shelf, near the shelf break. And then this, for the last several years, you can see the incredible freshening event at that location. This is the mean temperature. Sorry. All right. So this is the temperature. Sorry. So the incredible change temperature, the mean temperature in January. So I already mentioned that we have been developing the channel technology for a while, and this is just demonstration of what the capability. On the left, we deployed the sensor on the ROV off the Florida shelf to look at the carbon chemistry near coral reef, deep coral reef, at several hundred meters to 1,000. So this the profiles you see in the middle. You know, the 3,000 meter, 1 kilometer range of the DIC profile in 3D space. And then the right is we deploy this to map the DIC field in Waikua Bay, just off the WHOI. So we're in a process to adapt that kind of technology capability to the fishery base, to a low-cost sensor that we can use on fishing vessels. So and there are some objectives. On the right, this is the, as I mentioned, the CTD sensor, and up is the app, wireless app that can download the data from the CTD. So we kind of try to model this kind of capability. On the right, we already have a prototype pH sensor that integrates the electronics flow control system together, and this is fairly small. So hopefully we can deploy this soon, later this year, try it on something like fishing vessel listed here. So we are targeting the cost, less than $1,000. Okay, it will have the self-calibration capability. Okay, so we would try to limit any maintenance done by fishermen. So this can give them the total freedom to basically just deploy without worry about too much their time and effort. And then the sensor is targeting for high frequency, so we can do profiling. So as I mentioned, this is the scoping workshops. The goal is to bring together the key stakeholders and the collaborators across the fishing community, federal, state governments, technology companies, academia, with the aim to make plans to establish this network. First in the northeast coastal water. So my co-organizers include from researchers, scientists, and also the fishing community, as well as the technology company. So so if you're interested, let me know. So that's about it. So thank you for your attention.
Thank you, Alec. And can we have any questions?
Thanks, Alec. As you know, a lot of biogeochemical sensors drift, right? So in this kind of voluntary, fisheries observing vessel system, how would you handle, or what would a strategy be for validating those sensors?
Yeah, that's a great question. So I think, based on our experience, there's the sensor, you have to build a sensor with self-calibration or self-reference capability. So, in DO, we know how to do that, and when it's surface, right? And the pH will be a little bit different, but I think in general, I would say build the sensor around, have the capability to do self-calibration is the key. And then also we try to use the technology, require less calibration. So this is the pH sensor we're talking about, which is the spec principle instead of probe, which does drift. But I think the engineer is good enough now to make this more robust, even for a reagent-based method.
We can take one more very quick one, and then we'll
Jamie.
Jamie,
This is a very quick one.
Then we'll have time for the panel.
Do you pay the participants, or is it all volunteer?
I think it's, my understanding is we pay fishermen a fee. Not much, a few $100, if I remember correctly. So they do several cruises. Each cruise on the order of several weeks. Okay, and there might be also, a fisherman who really want to do this, and they don't want to get any money. They just want to try it. There's also that kind of, but usually we maintain this with a fee. So there's a build up, but that's still pretty cheap in terms of the ship time you get.
So maybe we can hold questions, and we'll try and get to the panel. But let's thank Alec again for the great talk. And as Alec said, this is an OCB activity, so just send him an email if you'd like to learn more about that activity. And so to bring us home today, it's a pleasure to move a little bit to the West Coast, shift back to the West a little bit, and welcome Clarissa Anderson from Scripps Institution of Oceanography, and also the director of the Southern California Coastal Ocean Observing System, who's going to bring us home with a talk on some ideas on the next generation coastal observing network for ecosystem monitoring and prediction. Welcome, Clarissa.
That's a mouthful.
Yeah.
You gave me that title. Thanks. Okay, I'm going to close this party out. I just want to say, because I don't have 3 hours to give this talk, everything that everyone said before is true. I would love to have said some of it in some capacity in relation to our work, but I can't. I mean, maybe the glider deck part might not be true, but we're going to work on that. Okay, so I know I don't have a lot of time, and there's a lot of material here. This opening slide is just meant to point out lots of people. We got our scientists, a lot of modelers over here, a lot of stakeholders. I've used this slide a lot, usually as it pertains to harmful algal blooms, so that's why some of the folks are here. But it maps to a lot of the things that we do, and you've heard a lot about that today. I'm pretty lucky that Adrienne gave a beautiful introduction to ocean observing and how it's structured. I thought it was kind of obvious to start with the GOOS definition. If you go to the GOOS website, this is what it looks like. And then there's many flavors of this take, depending on whether you're looking at a regional ocean observing system or a national level. For instance, if you go to the GOMO site, you're going to see this. Huge emphasis on the scientific understanding, but of course society plays a role in all of this. We have societal problems, we need to answer them. And generally, ocean observing systems are the call to arms for that. They're meant to solve that call to arms, I should say. This is the one for IUS, so I'll be focused a lot on the national US IUS network today. So you can see here that there is a focus on the people, the technology. You've heard so much about the technology in this session. And then developing the predictive tools that benefit directly economy, environment, public safety. The list goes on. Obviously, we cannot tackle all of these things perfectly, but we really do try. So here are, I don't know, does anyone here remember the WHO, one of the better acronyms that's come out of the last 15, 20 years? So one person, fantastic. And she's in ocean observing. So it is just fun to say. Anyway, so this came out of OceanObs 09. So OceanObs 09, if you can think back to that, and I'm sure many of you played some role in OceanObs 19. This framework for ocean observing was conceived, and it involved a lot of ideas, but it's a general idea that comes up a lot. We have feedback loops. We have requirements. They tell us a little bit of how we do the observations, structure the observational network. Rarely is that optimal. And then there's this generally some downstream products, and there's this feedback loop. I wouldn't say things have changed too dramatically, but one of the things that happened in 09 too was kind of thinking about how to codify, standardize our variables, think as a global community about ocean variables, EOVs, ECVs. Those I think we made a lot of progress on in the last 10 years. I think maybe the higher hanging fruit that's been a lot harder is the essential biodiversity variable thing that we're now moving into as we think about ocean observing now. So if you jump to OceanObs 19 in Hawaii, where we all sat and thought about that FOO in great detail, and tried to conceive of it in our newer frameworks where a lot has changed. You could really feel at that meeting that this is a fever pitch now. We need to solve these climate crises, and we need to come together in a real strong interdisciplinary way. And that's where images like this come from, which is how do we bring all of these biodiversity variables, process and rates and a rate exchange, not just biomass and abundance, but thinking about net primary productivity and moving into variables that we were not thinking about so much 10 years ago. But again, the feedback loop is still quite strong. We have requirements, but we need to figure out how to bring in the essential biodiversity component in order to tackle ocean health and ecosystem health and biodiversity questions. So there was actually, there were a lot of breakouts at that meeting. I was involved in one of those task teams. And what I want to show here is, you probably haven't thought about the Brotherton diagram for a while. It's been revised. And now we're thinking a lot about the Anthropocene as this big component of something that has clearly driven a lot of research, a lot of NASA and other agency investment for well over a decade. And now we're trying to bring in this human social dimension. And so much of that is happening in the coastal zone. And it's happening in the coastal zone and generally being tracked as some component of how it impacts ecosystem health, how it impacts biodiversity, and then what does that mean for, obviously, human health. And so I'm partly bringing this up here to say that I do think that as we go from global to coastal ocean science, we need to fully address these societal challenges and maybe break down barriers that might be cultural. I heard something about cultural barriers with industry earlier, but I'm thinking even about academic to applied cultural barriers. This is something we don't talk about a lot in this community, but there is an ivory tower thing that prevents this exchange. And now that I've lived in both worlds, I can very clearly say that there are interesting challenges when it comes to convincing people who focus so much on the beautiful Earth system science vision to figure out how to get all of that into the right places so that coastal ocean observing can evolve in the right way. And Mike Dietz really beautifully articulated the fundamental challenge of predictability and then how that relates to how predictability influences practical applications. And so this is just a little snippet from a recent paper, but basically saying making ecology or oceanography or meteorology, just put your field of choice in there, making it more relevant to policy management and decision making by better understanding what we can forecast, what we cannot forecast, and how we can improve those forecasts. And since I'm here to talk about ecosystem prediction on some level, I thought it was important to broach this topic of ecosystem predictability and what does it mean as we think about application. So now NOAA is very involved in pushing this model of service delivery. And there's nothing wrong with that. But what I have seen and what I have observed, and I think it's relevant for the OCB community, is that even when I'm in conversations that are strictly management-based and strictly focused on things like service delivery, there's a lack of recognition of how important that this box on the left is for that, and then also how important it is for this community to engage. And it doesn't always mean, I heard a lot today that I think was spot on about how this does not mean, especially what Jon said, that you have to then become an expert in all of this policy and management. That there's no way one person can do that. And if you're focused on good science, I don't think you can, but you do need to team up with the groups that do it, find the boundary organizations. Ocean observing systems like SCCOOS are kind of a boundary organization. We spend a lot of time doing that translation piece. So that translation piece is something where I encourage you, find your local OOS or other organization that does it, and try to make sure that your improvements to models are reflected in the service delivery piece at NOAA, because that is one way the downstream thing is going to happen, getting those improvements into the models in a way that's usable and useful. And so, for instance, if you look at something like the California Marine Protected Area Network and the very, very clearly defined need by the state to understand climate variability, vulnerabilities to biodiversity, there's no way that SCCOOS and the SCCOOS of the North, SCCOOS, the only way that the SCCOOS and SCCOOS can come together and create things like this is by having a very close collaboration with the modeling community in California, and this includes fisheries modelers, it includes the academic community, it includes NASA folks up and down the state as well who are distributed at places like Ames and JPL. So we come together in order to create products that might seem a little bit, I don't know, in one's mind, they could be detached from that kind of Earth system science, worldview, but they're not, because the models that are giving us this kind of picture at the bioregion and MPA level are coming from decades and decades of research to make Earth system modeling happen and make it accurate or highly skillful. So we need to start thinking about ocean observing in the future as having, these getting towards ecosystem conditions over a range of questions and activities. So I'll take another step back then and say one of the programs that was meant to kind of take ecosystem science to the next level, get it into the ocean observing systems, be kind of a valley of death. I would say, like, maybe not, you don't want to kind of call anything the valley of death these days, but you want to bridge the valley of death with programs that can say, how do we get all of the good R&D that's happening out there into the operational space, and how do we do that transition? And MBON was really meant to do this for a wide variety of science that gets at biodiversity, things like satellite-based estimates of biogeography. I'm thinking of like Maria Kavanaugh's Seascapes products, all the way to environmental DNA, codifying that into a system of best practices that then can go into monitoring programs and allow us to really assess biodiversity. And a lot of great stuff's come out of that program already, a lot of fruitful products that can help sanctuaries and fisheries have really nice automated reporting, infographics, the integrated ecosystem assessments and status report updates that you heard about. They all are going to rely on this sort of thing, and I think that has been helpful. But then what I would just say is that there is something missing, and I'm going to circle back to this towards the end of the talk. I think we need to think deeply about, and I'm not just singling out MBON here, it's one of many programs that could do this, but it's one that I think has been quite successful in thinking about this problem. But getting from all these ideas and truly getting them into our ocean observing system so that we can have a revolution in terms of what we see, the full ecosystem, end to end. Biology, you've heard so much about it today in this session, and I think we need to keep pushing on that. So in order to illustrate this, we'll focus on the West Coast. You've seen this map already in Adrienne's talk. We three, Jan, Henry, and I collaborate quite a lot. I think there's a little bit of a perception maybe that there's some insular quality, maybe a little too parochial sometimes, but we try really hard to come together and create a vision for the West Coast that gets beyond just maybe just the physics that a lot of these things were founded on early on. And so I'll touch on some of the things that are in yellow. So looking at partnerships, and there's a lot of partnership that goes on, as I just said. SCCOOS and SCCOOS come together quite a lot, more than I think most people probably recognize now. And if you don't know this already, the way IUCE works, you've got these 11 regional associations on the map that I just showed you. And we are kind of considered an extramural program of the National IUCE Office. So we write 5-year proposals, generally composed of a lot of the scientists and other service delivery folks and data operators in our regions. And usually, and this has been the case for a while, you are proposing 2 different levels. These might not be the best way to call this with the tiers because we put together one proposal, but in the end we get funded at the lower level for the most part because that's the way the funding has gone. But this level, which I'm going to get into a little bit later, this is the big vision. This is where you say, how do we make an end-to-end system? This is what it costs. And so we have jointly received at SCCOOS and SCCOOS, about we have a little bit of extra thing for extra projects, so it's a little bit over the $6 million mark. But between the 2 programs, that's what we're working with to try to do these, lofty things and promote coastal ocean safety, resilience, et cetera. And so you saw the map of our combined assets. I'll drill down just into SCCOOS right now to give you a little sense of the flavor of what we're doing. There's a lot of people involved, 22 principal investigators, 9 institutions. We put, I think that the statistic might be right, that for all the regions, we allocate the most towards the ocean observing, what's called subsystems. So we've got things like governance, data management, outreach, engagement, but one of the main subsystems, as you would imagine, should be ocean observing, and it is for us. That is how we can get this much out of it. But mind you, it is highly leveraged. That's been said a lot today in this session. So true. I mean, we couldn't do any of this stuff without leveraging the support that many of our PIs get from NSF, NASA, ONR, other programs like GOMO, you name it, the list goes on. But we managed to eke out quite a lot here, from radar to gliders to shore stations. I cannot talk about all of this stuff today, so I'm going to talk about a few flagship programs just as an illustration. For instance, the radar network. So in California, we have the largest high-frequency radar network in the world. This is for surface current measurements, real-time surface current measurements. As you can imagine, and this is a very busy slide, but as you can imagine, these data are assimilated into numerous models, data assimilative models that feed decision support systems for U.S. Coast Guard search and rescue, for oil spill response, both at the federal level and at the state level. We have tools that are used for pollution tracking at the Tijuana border. It's assimilated into a HAB model I'll talk about in a minute, so that helps the trajectories for that. And it's used frequently for studies of larval connectivity across MPAs. So it has a lot of uses. We invest a lot in this, but like has also been said about any ocean observing system, things start to fail and you have to recapitalize. So often our challenges, and this is the case with radar, is trying to revive one of the oldest and largest radar networks in the world and keep it going because it is highly relevant for our users. So this is like very clear service delivery. But if you're a modeler or a scientist, there's also countless ways to use these data. And that's what I would like to emphasize in this community. The California Underwater Glider Network, you've already seen some images. Both Grace showed you the spray glider. Susan talked about this and showed a map of the lines, line 90 being a very important line. So we support 2 of these lines, but again with the leveraging, ONR, GOMO, NSF. Like let's keep remembering that mantra. IUCE does not support all of this, but we did just put in this alongshore line, not on the shelf. True. We're having discussions about how to get these things onto the shelf. Grace mentioned Slocum's better for that. Spray glider does have some limitations when you get into very complex bathymetry, but it could be done and it can be done. But I want to say that this is an important program for capturing ecosystem predictability in the California current. You're getting a lot of great data on the heat content, the subsurface heat content, and a lot of other interesting connectivity to the equatorial Pacific, where if you look at the temperature time series with, say, ONI, you can start to see some really interesting changes over time. This huge departure from what's happening at the equator is the blob, for instance. We've also been in a pretty warm period since then that we haven't really recovered from. We're also experiencing a very interesting salinity anomaly in the last 4 or 5 years. So gliders are incredibly impactful at getting us to this next phase of ecosystem prediction. But then as has also been said, we've got to get towards how do we look at multiple stressors, everything that has been talked about at OCB this week. And that's through this bioeco-glider vision that Grace beautifully articulated, where we would love to build out every single one of these lines in this way. But right now, it's kind of based on, as a lot of things do start, these kind of ad hoc relationships with folks who have their own studies to do something, and you try to bring it into the fold and sustain it over time. And so you've seen that you can have these suites of sensors that are incredibly powerful at getting at the biogeochemistry in conjunction with the biology and start to look at those connections. So working with Dan Rudnick's group, Yui Takashita, and on it goes, we want to build out this vision that was in our 5-year proposals and think about how we can move this to the next level. And I don't have time to go through all those time series, so the meat of the matter is kind of coming out in a slide like this, where as we think about that model of service delivery, we have to start making as much use of our data as we can. And I think I've heard this in a lot of meetings that I've been to. We're not necessarily data limited. We're limited on the time and energy and the people to do the synthesis, the translation, to get things into people's hands in a way that they can digest it. And it does take, I mean, I know this almost sounds kind of trite to say it takes a lot of time to do that. It often takes dedicated people who have the domain expertise, but they want to spend the time doing this kind of work. And that's a tricky little niche to isolate, I think, these days. But I think more people are going into it. Often data scientists who do have domain expertise are interested in this. And so this is just one example of one of these things where, in a pan-regional way, SCCOOS, SCCOOS, and NANUS are working together to do things like create oyster dashboards. We now have money from the state to do an OAH portal and bring in many data streams, much in this kind of infographic way, as much as we do data that can be accessed via a table or a basic plot. And we're doing this in collaboration with shellfish growers and other fisheries managers and people at California Department of Fish and Wildlife, for instance. And so that's just one example where we're thinking, we try to do the lessons learned where a product is developed in one region, and then we expand it to the other regions, often because we share this California current, and we try to extend it and see what the utility and the skill is for those products. This is another one that's coming out of the coupled ROMS NEMRO runs that come out of UC Santa Cruz, so Chris Edwards' group with Andy Moore and Jerome Fichter and a lot of people who are getting some really great work. I'm not showing you the biogeochemistry coming out of NEMRO, but what you are seeing are things like heat content time series, rolling this in now into a marine heat wave product that tries to use like Hobday thresholds to isolate just what a marine heat wave might look like. And this will be useful to a lot of users, probably a little more on the academic side right now, maybe the policy side at the state level. But we're kind of trying to hit all of these different levels of users as we go along. So, for me, this is kind of the meat. I'll talk about HAB bulletins in a minute. That's another way that we're synthesizing a whole lot of information into one little nugget. But just to, again, emphasize how important the partnerships across these regions have been on the West Coast, when we wrote our last proposal, we actually spent a year forging a path where we would co-fund a majority of the work. And if you aren't familiar with the way the process of these the IUS Regional Association proposals work, generally you as a scientist would write an expression of interest to try to get into that proposal process. It doesn't happen on the back end, unfortunately, unless you do that through an extramural project that you write together. So thinking ahead and being strategic, we've been able now to generate 13 projects. The blue is funded by SCCOOS and SCCOOS. Everything in orange is our products that SCCOOS pretty much primarily supports. But it's a lot of stuff. I'm going to let you sit and try to absorb it because there's a lot to keep track of. But we're bringing in new PIs all the time. So we brought in Tom Bell to sustain and distribute his kelp biomass products from Landsat. We've also recently supporting, this was from an extramural project, not from our 5-year proposal, but trying to get in more and more into the grand synthesis and climate contextualizations for MPAs. So we have a dashboard that includes a whole lot of stuff, including getting just about every single nearshore benthic ecologist marine ecologists to give us data that's sitting on their desktops in various forms and get it into the portal and make it accessible to the state. So we're trying to ensure that, we can really transition a lot of stuff to operations, because some of these things end up being really useful. They go through the full cycle of, say, like in the case of this work, some NASA projects that funded it. But then it is hard to make that final step and get it into something to where it can be sustained. And more, we want to find the funding to do that. Another one of these extramural projects that we're working on collaboratively on the West Coast involves the West Coast Operational Forecast System. This is a new model that's come out of NOAA, Weather Service, Survey Development Lab, co-ops. It's distributed via that. It's Alex Karapov's model from OSU, but it's been extended now into the operational space. So we're looking at what are those impacts if you're going to leverage something like this, even though you've been supporting some other academic models, but now you might want to move into looking at WCOPS. What are the downstream impacts for the ecosystem forecasts that we have that are actually operational? EcoCast is one of them. We have quasi-operational ocean acidification forecasts, and we have another NASA-supported project that is operational for HABs. We're looking at that, and I'll focus a little bit on the HABs now because this is my baby. And this comes down to a model called CHARM. This was built off of years of NASA R&D and some NOAA support. There's that Valley of Death, cross the Valley of Death. It's now operational at NOAA Coast Watch, and it provides these spatially explicit nowcasts and 3-day forecasts of domoic acid. So the probability of encountering this really nasty neurotoxin is one of the bigger ones we care about on the West Coast for HABs, for public health, shellfish, fisheries, marine mammal management, you name it. And we're looking at what it means to, say, take something like this that was built off of MODIS optical variables, because this was built off of years and years of plumes and blooms data, getting lots of really great in-situ optics to constrain this model against the optical component, but then also forcing the spatially explicit picture with ROMS inputs, the physical inputs. And if we're going to move from one ROMS to another, we need to evaluate that. And just the same way, we're also evaluating the transition from satellite to satellite, because we've had to, as MODIS's life has ended, we have moved to VIIRS. We did that a little while ago, but part of the sensitivity analyses we're doing, and this is the same for every operational product that's out there, as you start to change the inputs and where they're coming from and the technology behind those inputs, you do have to keep doing this work. Even when something's been kind of birthed into operational space, I feel like it's really good to have that relationship with the people, the origin of those tools. And so you need to stay in the loop and help fix them and keep them up to date. So you're just seeing here some of the output of that sensitivity analysis. It's always nice when something falls a little bit above that one-to-one line in a receiving operator curve. It's better than flipping a coin. So we have, there's just a lot that goes into this. I'm not gonna sit on it, but the PACE early adopter program that you heard about from Susanne is using CHARM to think about how do we transition this to PACE sensors as well. And so this kind of HAB information is synthesized into a bulletin. Oh, and what I meant to say too on this has to do with the fact that we have a West Coast domain. So can we make CHARM a West Coast product? And can it be then integrated into the well-known Pacific Northwest Bulletin? We also have a California Harmful Algal Bloom Bulletin that could potentially be extended and merged with the Pacific Northwest Bulletin over time. But this is just another way in which we have to, as a community, think about synthesis. Our users really need to know how and why these models work, and they need to know that in relation to state data. We have a long-term HAB monitoring program, so we look at it in relation to that. Often, as you can imagine, what's happening at a pier is very, very different from what's happening both in the model and, say, what marine mammal strandings from domoic acid toxicosis look like. These things are so spatially decorrelated sometimes that it takes a synthesis product like this to allow someone to put the pieces together relative to the resource that they are interested in, because the shellfish grower is going to see and want something so different from a marine mammal rescue group. So, because I'm really running out of time, I want to say that we are, as I'm thinking about ecosystem prediction, how do we build this out? We're leveraging state resources to build an imaging flow cytobot network. Because we got 6 of those from state support, we have others from other academics, industry partners, and also from some foundation support. that Jeff Bowman is a part of with Andrew Barton and, and Dave Siegel, who you all know so well, is part of this too. We're trying to build out a vision of what could be next level ecological observing. Getting this level of phytoplankton data is extraordinary. It's gnarly to manage. I know this has come up. We talked a lot about interoperability earlier. We're thinking a lot about how to build a plankton DAC nationally. So this is an extramural project with folks from WHOI. Heidi developed the IFCB to try to harness this into something super useful for, at least for now, the national community, using Gulf of Maine and California as prototypes to say, how do you go from onboard operations into a database with a nice, front-facing page, do all of these kinds of products that others do not want to do themselves, and get these level 2 and 3 downstream products after you do the machine learning classifications, and then also funnel that into products that are being developed by other people that make visualizations just for the stakeholders, in this case, just for shellfish growers. There's a lot happening in this slide. I'm just going to have to keep glossing over these things, but I think you get the picture that as we move forward, we need to bring all of these different data streams in. So what does it take to get there? Well, I mean, obviously the flip answer would be $6 million a year, but really it just is code for how do we build this out. We got to have a real strategic approach here because everyone's underfunded all the time. And what we envisioned in that is so much what we heard about today, and it's the bioeco gliders. It's fishing vessels of opportunity. We actually are working with some of the same groups that Alec was just talking about. Conceptualizing deliberately, how do we do cross-shore and along-shore biogeochemistry with moorings, mini moorings from Uwe's group, outfitting the gliders, figuring out with the modelers what do they need and where do they need it, and trying to optimize the performance of these things. And really think integratively about how we do this and how it loops back on ecosystem prediction. And it's a huge challenge, and so far, most of the stuff you see here just remains in that space where we seek extramural support to build it out. So, what's missing from MBON? Well, it's been a great program, but we need to keep taking it to the next level and make sure that the funding that we're putting towards our concepts of biodiversity monitoring are going onto platforms where you can co-locate all of this stuff and truly advanced ecological forecasting. And so in that vein, the IUCE Association, led by Josie Quintrell, is working on a number of white papers, webinars, proposals to try to get Congress to pay attention to these themes. One of those themes is the coastal climate signal. So we already have that out. Dan was a huge supporter, promoter, inspiration for making that happen. We've had a webinar series. It's involved NMFS, OAR, GOMO, a lot of different groups. And so we're doing this for a whole number of ideas that we want to push forward and say, let's remember interagency partnerships are what's going to do this. So this is my last slide, just to point out that there's a lot happening at the global level. I'm sure a lot of you are involved in UN Decade programs. I'm involved in the one Megan Cronin is leading. And I just want to say that if we want to have these big ideas addressed, we need to start thinking that global to local picture and figure out how the UN Decade can push some of this forward and do it in a way where we're capacity building and thinking about mentorship and partnership. So these are my takeaways. Since I don't have a lot of time, I'll jump to this big idea. And this is also inspired by Dan, which is a thought about regional coalitions beyond NOAA. Think about these regional partnerships across the globe and how this could be a way to legitimize and also make things deliberate and intentional, like we've heard. Really, a lot of this stuff's accidental. Legacy stuff's accidental, but now we can be more deliberate about it. So I will just leave it there. Thank you. I'm sorry I went a second over there.
That was perfect. Thanks very much. Thanks, Clarissa. And John, do you need to? Yeah.
Well, that's
yeah. I was just going to say, if you had any thoughts you wanted to add before you have to rush off to Congress there, after hearing all this, or
I'll see if I can slip this in.
Great. Well, thank you. All right, thank you, John, and thanks again to Clarissa for a wonderful way to finish us off. That's not what we were saying. Finish us off. It's a valley of death kind of thing, right? Why don't we start with some questions for Jessica, but also call up the other participants and have them sit as well. But does anyone have some burning questions to start for Clarissa? Yeah. You're good.
Clarissa, it's Martina from the University of Technology, Sydney.
Martina.
Given the experience you've had in leading this program, can you tell us some of the critical ingredients of partnership success where you would say that this has been an excellent match between research user needs or forecasting or ecological prediction and the scientists, where that has worked so well? Could you identify characters of those partnerships for us?
There are quite a few, and because I'm so intimately engaged on the harmful algal bloom side, maybe I'll speak to that first, which is just to say that we have an incredibly tight relationship with both the discharge community that needs to monitor the nutrients that they put out into the community, the OTWs. One of those groups actually purchased one of the IFCBs in our network, and as well as the state public health experts. And so kind of moving across those, we not only provide them data and have a very tight relationship and feedback loop that goes into things like the bulletin, but more and more we're seeing investment from them. Like right now I'm working on a stable isotope project for food webs, and I'm seeing that these state public health groups actually saying, we had a little end of your money, we'd love to put it towards something that sounds really academic like stable isotopes, but they see the downstream power of being able to trace things like domoic acid through the food web. You know, briefly, that was just kind of a...
Thanks again, Clarissa, and thanks to everybody. I mean, I'm beginning to question my career choices of becoming a modeler after hearing all these great OBS talks. It was inspiring, to say the least. Jessica, did you?
I actually had a follow-up question to Martinez for Clarissa, but actually can be addressed by broadly the panel. So you commented on all these programs being chronically underfunded, and then when you partner with data scientists and people who build databases and all these things, they're often funded at a much higher level. How do you reconcile some of those needs? Like, what are some of the strategies that you use? And do you have any advice for us managing data, basically?
I think we need to start sharing some of the data platforms. You know, many of us use one data science company. I didn't go into that, but many of us at the region, we're all unique snowflakes. Got to remember that, and that can be problematic with regional work. However, there's an economy of scale that we need to embrace. Management, true, every stakeholder is unique too, and they might need you to throw some shiny apps up for them. That's different from the more, I don't know, canned stuff that you might get out of an economy of scale type model. But that's where I see the ability to do this, and typically it's a selling point for a lot of people to say, we already have this major contract with this group. You should work with us. It will go in there for very nominal cost to you. And so I don't know if that really answers what you're saying, but that's one of the ways, it's one of the strategies that we have.
So fire away with the panel questions. We threw up those questions just to get people thinking big picture across all the talks. And so, yeah, fire away. We've got about 17 more minutes. So we fit 20 questions into that time.
This is Lauren Cook from Rutgers University. My question is primarily directed to Alec, but also if there are any like NOAA people who also want to weigh in on my question. Alec, I think your initiative is fantastic. This is really exciting stuff for me as a fisheries background individual, and I think the overlay between bringing science and commercial fishermen participating in that science is a really great transdisciplinary effort to building trust between science and commercial fishermen. I was really curious, how do you advertise those opportunities to commercial fishermen or commercial companies? And do you do it through the State Department's websites, where they're probably often going? Do you approach them directly? And if you don't go through the state to advertise that, do you think going through the state or like NOAA could better build trust between science, commercial fishermen, and federal agencies and state agencies?
Great question, loaded. So for us, we just at a starting point, though physical oceanographer has been building this bridge for a decade or even longer than that, right? So they have the trust. The experience I heard from someone like Jim Manning or Glenn Gorkwich, who's a scientist at WHOI, they just first work with the Fishery Association, and then the Fishermen Association have their candidates who may be interested in measure seawater temperature, for example. They bridge that. They have to actually go out with the fishermen, talk to them directly, what may be the useful strategy for temperature, for example, salinity. So now they actually trust the scientists more than any agency. So now, because of that trust, we can go one step further, say, are you interested in oxygen or pH? Because this process already established, I think we can leverage that. But I think the timing is ready.
All right, we have a comment from the online from Sam Sodolecki. Just a comment, sorry it's so long. As has been pointed out by the speakers today, there are a lot of potential real-time observations possible to support ecological forecasting efforts. Reliable real-time observations within the coastal ocean are the most important type of observations we can make available to meet ecological forecasting needs for our current stage of this work. But one important reason has yet to be conveyed. This priority is critical as everyone is learning how to trust these coastal ocean forecasts, and these real-time observations are critical to doing just that. Within the weather forecasting arena, when there is a forecast for rain, for example, you make a decision maybe to bring an umbrella because you trust what's going to rain. This trust emerged from years of checking your phone or the news for the weather and then experiencing it later that day. We don't have a way to do this for ocean forecasts without the real-time observations that are easily accessible to all. And I know it's a comment, but I think some of the panelists might also have comments to add to that, possibly.
Already heard me say this before. One of the things I didn't say, this doesn't get at the real-time question, but one of the things I didn't say about the HAB bulletin, and that I often use that same analogy about rain, because when you have 60% probability of domoic acid risk above some level, depending on what you care about, you have to calibrate that. We've long moved away from uncertainty metrics and anything because it just didn't mean anything. But years and years of reading that bulletin and saying, oh, you know, at this pixel level, I see this relationship with the thing I care about, you do constrain into your own mental calibration. So it's not a real-time answer, Sam, but it is one that resonates. So.
Sorry, Julie Granger, UConn. So this is more thinking out loud, but I think as someone who's interested in processes and not a modeler, I have something to contribute with all these ocean observations. But I do feel a little bit that this is catering only to modelers. So we're creating all these data products to feed to the models, but I can contribute. So I would like to know how I could try and leverage, all my little NSF funding to do all this work. But what other sources of funding are there? NOAA is not available to me, and all these things to contribute here. From these observations, I can make real contributions.
Okay, I'll make a comment just from my experience in the offshore observing system. So I think our observing systems have to be built to feed science discovery and operational forecasting, and we can do it. I mean, they've done it in the atmosphere for decades. Most atmospheric science is done using gridded products, reanalysis products, actually. And we found in the tropical observing system study that Adrienne talked about, most of the science, if you look at most of the science of ENSO, is also done using gridded products. very few people actually look at raw observations. And that's going to happen in biogeochemical systems and probably eventually ecosystems sometime down the road. So that state estimate approach means that if the state estimate or the prediction is good, you don't need a mooring at every aquaculture farm because the state estimate gives you the observations at the farm, right? So you build the observing system to make the state estimate really good. So that's and you can do a lot of discovery using those things. But on the other side, the really other important part of these observations is to feed discovery, for sure. And so in the case of Argo, 5,000 papers, like things that have discovered using that data set that none of the people that started the program could even envisage people that would come up and use that data to make discoveries. So, and then the last thing I'll say is that there are processes in the models that we know are not well constrained. And so there needs to be dedicated observations, process studies, and campaigns that are going after those things. And they can be short, very intense, because they're going to challenge, you know, the parameterizations or inside the models, right? So there's a whole, you know, there's a whole set of things that observations can be used for and designed for. There's a subclass that has to underpin state estimation, but there's going to be classes of observations that drive discovery and process and phenomena understanding. I guess I'm stating the obvious, but yeah.
Just to build up what Susan said, I mean, I'll cop to one of my reasons for organizing this was the sense that there's a lot of that great science for discovery in this room, and that should not stop at all. I've always seen an opportunity with a few extra steps to also bring that science to decision space, to sort of the reanalysis space, and really help it reach its full potential. So I hope the message isn't, you know, kind of an either or. It's, geez, if we could just find the ways to connect the dots a little further, we could get so much more out of this. And I think that's true, you know.
Maybe I could follow up on those two sets of thought. I would say a lot of the ocean color observation is actually discovery driven. We do have a subset of operational products that get served up on our oceancolor.gsfc.nasa.gov site, and people use them operationally. Fishermen, for example, look for chlorophyll fronts, et cetera, and those are kind of proven science that translates well into things like fisheries forecasts, et cetera. But an enormous part of the ocean color remote sensing is actually discovery driven, and we are hungry for people to relate process driven hypotheses and mechanisms to what we can observe from space. So at a practical level, I think I heard you ask, where could you get the money, the funding to actually use some of those direct observations? A lot of people don't think about NASA funding calls as being relevant to Earth or ocean science, but there are actually a lot. If you look at some of the ROSES funding calls, they're really relevant to blue skies discovery, physical oceanography phenomena, biogeochemical processes, phytoplankton ecology, and all of those things are the signals are there in the ocean color measurements that we make. So that is a tangible mechanism that you can use for sure.
All right, I actually have the mic and a question for Clarissa, so I'm going to take this opportunity since I'm standing here. So my question has to do with what you put up right at the end is the beautiful work that you guys are doing to create like an IFCB network and working with Heidi and you know I've seen lots of talks more recently where you know there are IFCBs that are in lots of other places like you know associated predominantly with harmful algae blooms and other things is how does someone who has one, we have one at ODU that Sophie Clayton runs, like, you know, how can we leverage getting that into the bigger network? And is there a way to also take advantage of the planktoscope, which is not at the same scale, but make something for that, because now we can, using, I don't know if anyone's heard about the planktoscope, but it's like open science for building like a little mini AFCB. They're awesome.
GoPro.
Can you speak to that?
It's not the same as an IFCB, let's just be clear. Jessica and I actually were talking a lot about this exact topic. It's a really good question. So the DAC, the HAB DAC / plankton DAC that I was referencing, it's still in its infancy. So it's not ready for everyone to start giving their data over. It will be, that's the hope, that's the vision. And the vision is that it doesn't stop at IFCB data. It's meant to primarily serve the HAB community first, because that's where a lot of the funding comes from. And I call the rest of it kind of the Trojan horse. It's going to come in underneath it. But the HAB part means that you want to bring in toxin data, you want to bring in other monitoring data. So we have a vision, and one of the beauties, actually this gets to Jessica's question earlier, of working with a group like Axiom Data Science that has the entire IUCE catalog in their framework already, is the layering and the co-location that's already inherent. It includes satellite fields and in-situ fields. But we're hoping to make it appealing to people to put their data into this framework so that your data get managed, they have backups, and then you have all of these added value products that you wouldn't have had otherwise. And if anyone bought an IFCB, they know just setting up the dashboard can be a pain. And so we would be providing all of those services. Will be, not would, will be.
Can I just comment on your question really quickly that we also have, we're working with Clarissa on this NOAA-funded project to build a database of plankton size structure using IFCB, FlowCam, ZooScan, UVP, all the way up to ISIS to kind of look at the whole, like not the whole range of plankton, but a large chunk of the range of plankton, and we'll be serving it up in a NOAA database managed by NIMS, and so it will be totally open, and then we'll also make the workflow totally open as well.
That's another GFDL person in the observing space.
Hi, Zach Erickson, NOAA PMEL. I have a question, I guess, first for Adrienne, but for anyone. I'm wondering that we've talked about a lot of different platforms, and even when we're talking about a platform that's pretty common, like gliders, there's sometimes difficulty in finding the data. But sometimes we're talking about just huge numbers of platforms, many of which aren't even owned by the scientists who use them. How do we make all of those data, fair? And I'm thinking especially findable and accessible.
Yep, another big challenge. And this is something that we're grappling with surface vehicles, right? Because they all have a different model, and in some cases, you're trusting a company to deliver data to you, which is a model that we get satellite products that are kind of that model too. So I don't have a good answer. I think that it requires a lot of people power, and you have to work through all levels of making sure that the data quality are good, that the format is machine readable, like Susan showed. They'll go to the same place in the same format. They all are associated with metadata. All of that is just a lot of work. And I don't know that I've been to the IUCE website in a while, but I liked that you put that up on the screen, because the part of the IUCE mission was people and technology, but people was first. So I think a lot of people power needs to go into that problem. And like I said, we often overlook and underfund that piece. Yeah, so it's a challenge.
Yeah, I'll just make one comment. As Adrienne said, this is expensive. And I think it's really hard to build an observing system on a volunteer basis. That's really difficult. I mean, it's great, but I would say on the physics side, a lot of our research campaign data goes into a black hole. Mooring data is a perfect example. And so my personal opinion is we need a backbone of really funded, real-time documented data streams where there are groups that are funded to manage the data and get it to the operational centers and the research community in a known way, and they are checked, and there's metrics and all of those things. And so, yes, I think, the community research-based campaign data coming in is really valuable, very important for the discovery side, and reusing that data is really important. But for a backbone system that's underpinning state estimate and prediction, I think that has to be funded as such. It's going to be very hard to do it in a kind of campaign-based way, I guess. That's just my personal.
Yeah, I'll just speak to some of the glider. Well, it's all of the observation system, and Clarissa might be able to add to this, but I use the Integrated Ocean Observing System, just rolled out like a data certification program over the past, 5 years or something. Oh, okay. Oh my gosh, time's flying fast. And it's basically, they initiated it just so that people will actually trust the data that's coming from IU's platform. And so every region has the certification process, and I think all the regions are certified now. Yeah, something like that. Yeah, but that incorporates, data quality control of all your sensors to the highest community-backed practices. That incorporates your data management. And IUS has a great backbone, although something's broken. But it has a great backbone to where, all the data is being put for the gliders, for instance, is being put into a glider dock, and that's all the delayed mode quality controlled data that can be accessed. It includes the near real-time data as well, but then we can also upload our quality controlled delayed mode data. So we have a data management system, and again, it does go down to the people. Most of our funding in those regional ocean observing systems are people that are really handling the data management. So I feel like we've made some progress, especially with at least through IUS for the certification process. So I don't know if that helps at all, but we have more work to do, of course. But
I gotta say a little bit different way. So I show the data, that's physical data, salinity temperature, and it's good quality. And you actually can capture the warming and shift of the system, the northeast. I think it's just, if we do it right, the community base can provide a very valuable, even long-term observation. That's why we want to have this scoping workshop to involve a data management company, and scientists and all the fishermen association together to come up with a plan that everyone can agree on it, and then including the data quality, and then the calibration included. So I think we just need to try it. As long as they have the willingness, want us to join them, I think maybe it works.
I wasn't, when I said community-based, I wasn't referring to the fisherman-based thing, because that would be a program with, goals and sampling. I'm talking about using research campaigns as an observing system. I think that's a lot harder because research funding is 3 years. It's usually focused on a phenomena, and that doesn't replace a sustained, deliberate observing system, which is what you're talking about.
Let's go with one more question. It looks like I just saw the microphone go out, so you bring us home.
Well, I'm going to bring us home. That's wild. Bethany Jenkins, University of Rhode Island. This is really a question for Clarissa, but the rest of the panel, kind of following on the conversation we had yesterday about building these large programs. And I know some of those scientists you spoke of in terms of their connections, and there's a lot of people with a lot of skin in the game. So how do you build and sustain that community for the work that you were talking about? And I just wanted to know if you could share some of those thoughts in terms of ground up for some grand program.
Yeah, that's a tough one. So I think most people here can appreciate, and I tried to get to this on the last slide, that legacy that exists, that that comes out of some of the grassroots efforts that formed the backbone of these regional associations back when. You don't want to start a time series and then stop it. So you've got people who are now kind of grandfathered in to this sort of base operation. And they do a lot of skin in the game, so those time series get longer and longer. But then you have to contend with the fact that you may have a vision. You want to deliberately build this out a certain way. You've got to bring people in the right way and hope that you will continue to have the operations and maintenance money to support them. So it's a leap of faith. And I think you probably, the way we've done it is bring people in at pretty small level of support and try to build on that through time and hope that they become part of that bigger family and network and see the value of it. I don't know if this answers your questions. I mean, the strategies vary across each RA, but I know that for California, because we have such an incredible scientific community, we want to build on that absolutely as much as possible and keep people funded as long as we can. Challenges really there.
Great. Oh, well, yeah, sure, go ahead.
In terms of legacy, I think we also need to think about how the next generation of scientists are really different than the folks sitting up here. And I've talked to a lot of the young scientists here, and I mentor students, and I hear their goals, they sound a little bit different than my generation's goals and the generation before me. And they're also growing up in a different planet, and they're feeling climate grief. And that's not something that we, came up feeling. And I think we need to think about how we need to think about how our science culture kind of evolves over time, and we keep these, observations and research going in a way that sustains them, and they don't leave the field because they're burned out. And I don't have the answers there, but I just think that's something that we need to think about.
Like a critical point to end on, not just sustaining the office, but sustaining the community, right? And so maybe with that, we can thank this wonderful set of speakers today.